3i Atlas was never supposed to do anything. It was meant to be silent, a frozen relic from another star, drifting through our solar system on a predictable arc of light and dust. But on October 29, 2025, as it skimmed past the Sun, it broke every rule written for comets. At first, the instruments showed nothing unusual. Then, in a single frame, everything changed. A sudden flare, sharp, geometric and impossibly bright, erupted from 3i Atlas's surface. Within minutes, 3 observatories across 2 continents confirmed the same signal. What looked like a calibration glitch became an event. What looked like a comet became a question. For 20 minutes, 3i Atlas burned 4 times brighter than physics allowed. Then it collapsed into silence, its light curved flat, its orbit subtly shifted, as if it had felt the sun and pushed back. In control rooms from Pasadena to Darmstadt, scientists froze over their consoles. The data was clean, the geometry was real. And buried in that 20-minute spike was a pattern no one could explain. Symmetry where randomness should live, precision where chaos should reign. From that moment on, 3i Atlas stopped being a rock from deep space. It became an anomaly, a message written in light from something that was never supposed to speak. This is the 3i Atlas channel, calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to enter the giveaway for our exclusive 3i Atlas hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. At first, it looked like a calibration error, a pixel flare, a data glitch from solar interference. But when 3 separate observatories confirmed the same reading within minutes, disbelief turned into silence. Something had happened near the Sun, something that none of the predictive models for 3i Atlas had accounted for. The interstellar object, expected to follow a stable brightening curve as it rounded perihelion, suddenly surged in luminosity by a factor of 4. The spike lasted just under 20 minutes before collapsing into a flat line, leaving behind a riddle written in light. To understand why this was so alarming, you have to understand what should have happened instead. When a comet approaches the Sun, the rising heat causes its surface ices to sublimate, venting gas and dust into space. The result is a coma, the bright envelope that makes comets so striking, and sometimes a tail that streams away from the Sun. This process is predictable. As distance decreases, activity increases. Then, once the comet passes closest approach, the sunlight lessens and the object begins to fade. That's the curve every known comet follows. 3i Atlas did not. The moment it hit its perihelion distance, around 0.17 astronomical units, the expected outgassing should have peaked smoothly. Instead, telescopes recorded an instantaneous jump in brightness. The light wasn't diffuse like a growing halo. It was sharp, sudden, concentrated. In scientific terms, it resembled an optical flare, an outburst of material that releases far more energy than solar heating alone can explain. One instrument described the pattern as a non-thermal release, meaning the energy output exceeded what could be accounted for by simple temperature change. At the same time, solar monitoring satellites detected a spike in ionized particles traveling outward from roughly the same region of space. But because 3i Atlas was nearly behind the Sun from Earth's perspective, direct visual confirmation was impossible. Every frame captured by the LASCO coronagraph aboard SOHO showed only the faint edges of the event, like watching lightning through a curtain. The few visible moments showed a spherical expansion of gas, followed by a rapid collapse into a tighter, dimmer structure. The light curve flattened, and when the glare subsided, the object appeared dimmer than before. Astronomers began to theorize. The most conservative explanation was structural venting, a sudden rupture of internal pressure within the nucleus. If the interior contained pockets of frozen carbon dioxide trapped beneath an insulating crust, the immense heat from perihelion could have caused those pockets to explode outward, momentarily increasing brightness. That would fit the known composition. This comet was rich in carbon dioxide, far more than water ice. But even that model fails to explain the geometry of the expansion. Plasma physicists noticed something else. The burst displayed angular symmetry. Instead of a random plume, it expanded in 6 primary directions, hexagonal, faintly geometric. That pattern can appear in magnetized plasma when charged particles align along magnetic field lines. In simpler terms, the burst might not have been entirely chaotic. It might have followed the magnetic topology of the solar wind itself. If that's true, then the sun didn't just heat the comet, it interacted with it. What makes this event even stranger is what came next. Following the outburst, the comet's trajectory shifted slightly. The eccentricity of its orbit decreased by a measurable fraction, as though it had exchanged momentum with something unseen. That should be impossible without an external force, yet the orbital data, confirmed independently by ESA and NASA, show the change is real. Either the mass of the nucleus redistributed internally, causing its spin to alter, or the burst imparted thrust strong enough to modify its motion. In either case, the burst was not just a visual anomaly. It was a physical event that left fingerprints across multiple datasets: optical, infrared, and magnetic. It was energy released faster than theory allowed, shape formed where randomness should reign, and silence where noise was expected. When the data came, through that night, a senior scientist reportedly whispered 3 words that captured the mood across observatories worldwide. That shouldn't happen. Yet, it did. And now, as 3i Atlas drifts away from the Sun, the question remains unanswered. Was this a natural detonation of trapped volatiles? Or the first sign that something inside the object behaves according to rules we haven't written yet? Every planet, asteroid and comet bound to our solar system obeys the same invisible rule. Gravity holds them in orbit. They circle, they return, they repeat. But 3i Atlas never belonged to that club. From the moment of its discovery, its path through space told a different story. Its orbit was hyperbolic, not elliptical, not even parabolic, but open. In mathematics, that means one thing: it's leaving, and it's never coming back. When astronomers plotted its trajectory in July 2025, the numbers didn't lie. Its eccentricity, a measure of how stretched an orbit is, was greater than 1. For bound objects, that value is always less than 1. Anything above it is an escape path. Through Atlas wasn't looping around the Sun. It was cutting through the solar system like a stone skipping across a pond. It entered from deep interstellar space, curved under the Sun's pull, and will exit again, never to return in any human lifetime. That alone would have made it historic. Before Atlas, only 2 confirmed interstellar visitors had ever been recorded: Oumuamua in 2017 and Borisov in 2019. But Atlas was different. Unlike its predecessors, it arrived on a trajectory almost aligned with the plane of the planets, just 5 degrees off the ecliptic. That angle is statistically rare. Most interstellar bodies wander in from random directions, tilted steeply relative to the solar system's disk. Yet this one seemed to know the route, slipping between the planetary lanes like it had rehearsed the maneuver. The first calculation showed something else unusual. It was moving retrograde. While every major planet orbits the Sun counterclockwise, as seen from above the solar North Pole, Atlas was moving clockwise, against the traffic of the entire solar system. That reversed motion complicates gravitational interactions and makes close approaches even rarer. In other words, this object didn't just appear foreign, it moved foreign. At its inbound velocity of roughly 42 kilometers per second relative to the Sun, Atlas carried the fingerprint of another stellar nursery. Spectroscopic analysis from the James Webb Space Telescope later confirmed that fingerprint, carbon dioxide dominating its composition, far more than in any comet ever catalogued here. Its chemistry was alien, and so was its behavior. Even hundreds of millions of kilometers away, before solar heat could work its magic, it was already active, venting gas, glowing brighter, ignoring the distance thresholds that keep ordinary comets dormant. When it finally swung inward, astronomers expected a predictable increase in brightness followed by gradual fading. Instead, its light curve fluctuated erratically, pulsing every few days in a rhythm that didn't correspond to spin or outgassing cycles. It was as if the object's own structure was breathing. These oscillations led some researchers to suggest internal layering, alternating shells of volatile ices and refractory minerals that vaporized in sequence, creating bursts of activity. Others whispered a stranger possibility: resonance with solar magnetic fields, a phenomenon never before observed in comets, but theoretically possible in plasma-rich environments. During its approach, planetary defense networks tracked its path obsessively. At its closest, Atlas came within 0.19 astronomical units of Mars, close enough for gravitational nudges, but far enough to rule out collision. Still, its motion showed subtle deviations, small but real. They couldn't be fully explained by outgassing thrust. Something about its mass distribution didn't fit the model. That's when the term hyperbolic stranger began to circulate through observatory logs and internal memos. It wasn't just a comet. It was a messenger from a region of the galaxy where chemistry, temperature, and cosmic radiation shape matter differently. It carried within it the memory of a different star, a different epoch, perhaps even a different kind of planetary system. By October 29th, when the object reached perihelion, its status as an interstellar body was no longer in doubt. The data confirmed it had originated far beyond the Oort cloud, likely ejected from its home system millions of years ago. It had travelled light years through the dark, gathering cosmic dust, radiation scars, and secrets we have no instruments to read. Now, as it departs, fading into the outer void, 3i Atlas becomes both a visitor and a teacher. Every photon it reflects carries the chemistry of somewhere else, a place we may never reach. It reminds us that the sun's gravity, dominant as it seems, is just one voice in a much larger choir, and every once in a while, one note, a hyperbolic one, drifts through, sings its brief, strange song, and disappears forever into the silence between the stars. Comets are often called dirty snowballs, and for good reason. Their cores are made primarily of frozen water mixed with dust, rock, and organic compounds. As they approach the sun, that ice sublimates, turning directly from solid to gas, and forms a glowing cloud called the coma. Water vapour is always the dominant component. Always, until now. When the James Webb Space Telescope first turned its instruments toward 3i Atlas, scientists expected to see the familiar chemical signature of water-based sublimation. Strong emission lines from hydroxyl radicals, traces of hydrogen, and ultraviolet fluorescence typical of H2O vapour. Instead, what they found was something almost unheard of, a coma dominated by carbon dioxide. The ratio of carbon dioxide to water was roughly 8:1. That is, for every molecule of water, there were 8 molecules of CO2. In cometary science, that's an anomaly so extreme that it forces every model back to the drawing board. Carbon dioxide is volatile at much lower temperatures than water ice. It begins to sublimate hundreds of millions of kilometers farther from the sun than water does. That means 3i Atlas began venting gas long before solar heat could have melted traditional ice. In early observations at nearly 3 astronomical units, almost 3 times the distance between Earth and the Sun, the comet was already releasing enormous quantities of vapour. By all accounts, it was awake, far too early. One theory suggests that 3i Atlas was formed in a region of its parent star system much colder than anything inside our own Oort cloud. There, water may have frozen so deeply within the core that it never reached the surface, while carbon dioxide accumulated closer to the exterior. If that's true, the object is effectively an inverted comet, a body with its chemistry flipped inside out. Its volatile materials are layered in ways that no solar system comet would naturally develop. The unusual composition also explains part of its strange behaviour near the sun. When CO2 sublimates, it expands with far more force than water vapour, generating intense localised jets that can change a comet's rotation or even fracture its nucleus. But the expected side effects, erratic acceleration, visible fragmentation, didn't happen. Despite the violent venting, 3i Atlas maintained relative stability, with only minor trajectory shifts. That contradiction puzzled astronomers. One possibility is that the nucleus is denser and more cohesive than expected. A CO2-rich crust over a rocky or metallic core could absorb internal pressure without breaking apart. In that case, the carbon dioxide would escape through narrow fissures rather than erupting in chaotic plumes. This could also account for the symmetrical jets seen during the outburst near perihelion, a form of controlled venting rather than random explosion. The absence of water lines in the spectral data carries another implication. It means that the surface temperature of the nucleus never exceeded the point needed to liberate water molecules, even at perihelion. The sun's heat should have been enough to melt any exposed ice. The fact that it didn't suggest one of two things. Either the water is sealed beneath an insulating shell of carbon dioxide frost, or it simply isn't there at all. The latter would make 3I Atlas the first major comet ever observed with almost no accessible water content, an object fundamentally different from anything in the solar record. If it truly lacks water, then our definitions collapse. We can't call it a traditional comet, because the driving mechanism of its activity, water sublimation, is missing. Yet it behaves too dynamically to be classified as an asteroid. That ambiguity forces scientists to revisit how they categorize small bodies in general. The old taxonomy, asteroid, comet, interstellar visitor, may no longer be sufficient. This imbalance between carbon dioxide and water also changes how sunlight interacts with the object. CO2 absorbs and re-emits infrared radiation differently, creating a distinctive thermal profile. It can trap heat beneath the surface and then release it in pulses, which might explain the flickering brightness pattern detected during its approach. Each pulse could represent a breath of trapped gas, building pressure until the crust gives way again. In a sense, 3I Atlas behaves more like a pressure vessel than a snowball, a sealed chamber storing volatile gases from another solar nursery, releasing them only under the most extreme conditions. Its lack of water doesn't make it less interesting, it makes it revolutionary. Because in the history of cometary observation, we've always assumed water was the universal solvent of motion, the baseline of activity. But 3I Atlas has rewritten that rule entirely. Carbon dioxide without water shouldn't produce a living, breathing comet. And yet, here it is, glowing, spinning, and bursting near the sun, teaching us that even the coldest chemistry from another star can find new life when it meets our light. When the outburst began, it didn't look like an explosion in the conventional sense. There was no asymmetric plume, no chaotic spray of debris spinning into space. Instead, telescopes watching through the sun's glare caught something eerily symmetrical, a smooth, geometric swelling of light radiating outward from 3I Atlas, as though a transparent sphere had suddenly inflated around it. Astronomers called it the shell. It expanded fast, then stopped, frozen in place for several minutes before fading. What they saw defied every known behavior of a comet near perihelion. In most comets, sublimation happens unevenly. Jets erupt from random vents across the nucleus, shaped by fractures, shadows, and rotation. Those jets collide, disperse, and eventually form a chaotic coma, a fuzzy, irregular envelope of dust and gas. But what happened around 3I Atlas was different. The expansion was uniform, controlled, and structured. Instruments on the solar orbiter measured the boundary of the glowing shell at nearly 20,000 kilometers wide, vast but too sharply defined to be ordinary outgassing. The light itself wasn't just scattered sunlight. Spectral data indicated high excitation levels of carbon dioxide ions, specifically CO2 plus emission lines that appear when molecules are stripped of electrons by extreme ultraviolet radiation. In simple terms, the comet's carbon dioxide didn't just evaporate, it became plasma. The result was a thin, magnetized shell of ionized gas expanding into the solar wind. But the geometry puzzled researchers. The shell's outer edge wasn't perfectly spherical. It exhibited 6 faint ridges, a hexagonal pattern faintly visible in coronagraph imagery. In plasma physics, hexagonal symmetry can emerge from standing wave interactions, where electromagnetic forces balance in stable configurations. These so-called plasma cells have been recreated in laboratory environments, but never observed naturally around a comet. The coincidence of geometry, symmetry, and timing suggests the event wasn't random. One theory proposes that the carbon dioxide gases vented from multiple fissures in phase, triggered simultaneously by a sudden change in the comet's rotation or internal temperature. If pressure had built evenly throughout the subsurface layers, the surface could have fractured along natural stress lines, venting gas uniformly. The effect would resemble a synchronized detonation, a controlled expansion rather than an explosion. In this model, the hexagonal ridges correspond to interference zones, where colliding jets of gas stabilized against one another. Another hypothesis ventures into electromagnetic territory. The Sun's magnetic field near perihelion is a turbulent ocean of charged particles. When a dense pocket of plasma enters that region, it can form temporary boundaries, magnetopauses, where the solar wind and the object's own outflow balance forces. If 3I Atlas released a massive burst of ionized carbon dioxide, the solar wind could have shaped it into a magnetic shell, compressing and flattening its poles, giving rise to the hexagonal pattern. The process is fleeting, a magnetic bubble, lasting only minutes before dissipating into the solar current. Whatever the mechanism, the scale of the shell expansion carried measurable consequences. The event temporarily altered the density of solar plasma in its vicinity. Parker Solar Probe data showed a subtle but real drop in proton density downstream of the object's trajectory, as if the expanding shell had displaced part of the solar wind itself. That implies energy transfer on a scale far greater than thermal venting could provide. The calculations suggest an instantaneous energy release equivalent to several terajoules, small by cosmic standards but enormous for a kilometre-sized body. Then there's the aftermath. Once the shell dissipated, 3I Atlas didn't fragment as expected. Instead, it appeared dimmer but intact, as though the event had peeled off a layer rather than shattered the nucleus. Some astronomers likened it to a molting process, the comet shedding its outer skin. This interpretation fits with the light curve, the initial spike, the plateau, and then the sudden decrease in brightness, corresponding to a reflective layer dispersing into space. That shell may have been more than gas. High-resolution photometry detected fine particulates within the expanding envelope, micron-scale dust grains coated with frozen CO2 crystals. Those crystals would sublimate rapidly under solar heat, contributing to the bright flash, while the dust lingered briefly before scattering. In effect, the shell was a bubble of vaporized carbon dioxide carrying a halo of microscopic mirrors that amplified the light before fading. The event lasted less than half an hour, but it changed everything we thought we knew about cometary structure. Before 3I Atlas, no interstellar visitor had ever displayed such symmetry or such composure under solar stress. Natural or not, the shell expansion revealed that this object's surface isn't merely reactive, it's responsive, capable of uniform behavior under extreme conditions. For a brief moment near the Sun, 3I Atlas stopped behaving like a comet and started behaving like a system, a body that releases energy in patterned waves, as though the universe had pressed a button we didn't know existed. The shell faded, the light dimmed, and the object continued its outbound flight. But for those few minutes, the void shimmered, structured, deliberate, and alive with the silent pulse of geometry. On October 29, 2025, the Sun released a coronal mass ejection, a vast eruption of charged plasma thrown into space at hundreds of kilometers per second. It wasn't remarkable at first. Solar ejections happen daily, some minor, some violent. But what caught attention wasn't its size, it was its direction. The CME emerged from the Sun's southern hemisphere, right along the trajectory of 3I Atlas as it reached perihelion. Hours later, the comet burst. This coincidence, recorded by 3 separate space observatories, quickly became the focus of investigation. Could the CME, a storm of protons, electrons, and magnetic fields, have triggered the sudden outburst? And if so, what does that mean for how comets interact with solar plasma? To understand the puzzle, we need to examine what a coronal mass ejection actually is. A CME is not just light or heat, it's matter. Billions of tons of magnetized particles hurled from the Sun's corona into space. When one of these ejections crosses a planetary orbit, it distorts magnetic fields, compresses atmospheres, and sometimes disrupts communications on Earth. Normally, when a CME passes a comet, it produces a visible reaction. The tail bends, the coma flares, or sometimes, as with Comet NK in 2007, the tail is completely torn off. But in the case of 3I Atlas, the reaction didn't resemble any known CME comet interaction. Instruments tracking the solar wind detected an impact at roughly the same moment the comet brightened by 4-fold. The CME that struck it wasn't particularly strong, category C by solar standards, yet the energy released from the comet exceeded what the solar particles could directly account for. That means the CME didn't simply push or heat it. It triggered something. One model suggests that the incoming plasma acted like a detonator. The surface of 3I Atlas, already under thermal stress from the Sun's radiation, may have held regions of highly pressurized carbon dioxide ice just beneath the crust. When the CME's magnetic field swept across the object, it could have induced electric currents through the conductive material in the nucleus. Even a current of a few milliamps per square meter would generate localized heating. Multiply that by the comet's surface area, and you get rapid sublimation, enough to rupture the crust. This mechanism isn't theoretical. During laboratory simulations of comet analog materials exposed to charged particle flows, researchers have observed electrostatic discharges and surface explosions resembling miniature lightning strikes. These occur when a conductive path forms through the volatile ice layers, releasing trapped gases violently. For a CO2-dominated body like 3I Atlas, such a chain reaction could ignite across multiple vents at once, explaining the symmetrical shell observed in the aftermath. Another possibility lies in magnetic resonance. As the CME approached, its magnetic field oscillated at low frequencies. If the internal structure of 3I Atlas contained layered deposits of differing conductivity, those oscillations could have induced resonance, a brief coupling between the external and internal magnetic fields. The resulting stress might have fractured the nucleus from within, causing the observed energy release without direct impact. Solar physicists point out that this was the first known instance of a CME interacting with an interstellar object. Every previous event involved comets born in our system, bodies shaped by the same composition and magnetic behavior as local matter. But 3I Atlas came from elsewhere. Its plasma response may not follow the same rules. Its carbon dioxide envelope, for instance, would ionize differently than a water-rich coma, allowing electric charge to accumulate rather than disperse. In such conditions, a CME could produce not just mechanical force, but electrical breakdown, a cosmic-scale short-circuit. The timing supports this. The LASCO C3 coronagraph recorded the CME front reaching the comet's location at approximately 1436 UTC. At 1438 UTC, the light curve spiked. By 1450, the brightness plateaued, then declined. No other event in the solar environment matches that timeline. The burst wasn't random, it was synchronized. When data from the Parker Solar Probe later arrived, it revealed a shockwave ripple in the solar wind density near the same coordinates, consistent with a plasma object interacting resistively with the CME flow. In essence, the comet pushed back. What makes this interaction remarkable is not just that it happened, but that it was measured. For the first time, we witnessed energy exchange between an interstellar traveller and our Sun, a collision not of bodies, but of magnetic intentions. The CME struck, the comet responded, and for 20 minutes, both systems sang the same tune. Whether it was coincidence or communication remains open to debate. Some scientists interpret it as a natural resonance between solar activity and a volatile surface under stress. Others wonder if 3I Atlas simply reacted too perfectly, as though tuned to the Sun's pulse. Whatever the truth, the CME connection turned a routine solar eruption into one of the most perplexing moments in recent astronomical history, a handshake across cosmic origins, written in plasma and silence. The story of 3I Atlas's perihelion isn't just about what we saw, it's about what we didn't. For almost 20 minutes during the comet's closest pass behind the Sun, the Solar and Heliospheric Observatory, SOHO, recorded nothing. The data gap begins precisely at 1437 UTC on October 29th, right when the brightness of 3I Atlas spiked. When the stream resumed, the comet's coma was visibly altered, and the background plasma field around the Sun appeared subtly rearranged. Those missing frames, now catalogued in the official LASCO archive, became the most controversial data silence in modern solar observation. To the untrained eye, it might sound like a glitch, and perhaps it was. Coronagraphs like LASCO, the large angle and spectrometric chronograph, regularly enter protective modes when the Sun's radiation overwhelms the sensor. When that happens, the system automatically pauses imaging to prevent damage. NASA engineers say this is routine. In the words of mission scientist Carl Battams, if the Sun brightens too sharply, or an object saturates the field, the camera locks down. It's not a cover-up. It's just safety. But the problem isn't the explanation, it's the timing. These protective events usually occur during massive solar flares or particle storms. On October 29th, no such disturbances were detected. The solar flux index remained stable. There was no X-class flare, no radiation spike, and no communication blackout. The only event of note, Anywhere near that window was the outburst of 3I Atlas. So why did the cameras go dark exactly then? Analysts at the European Space Agency reviewed the telemetry logs. The data shows that LASCO's exposure settings suddenly saturated, exceeding threshold limits by a factor of 7. The automatic safing sequence kicked in and froze imaging. When the system rebooted 20 minutes later, the brightness had already normalized. This sequence matches what would happen if something extremely bright, brighter than the sun's corona in localized pixels, had entered the frame. But what could shine that intensely, even briefly, without triggering similar responses on other sensors nearby? The answer remains uncertain, and that uncertainty feeds speculation. Within hours of the data release, social media was ablaze with claims of censorship. NASA deleted perihelion footage, one viral post read, accompanied by screenshots of the missing timestamps. YouTube channels drew red circles around static frames, insisting they showed a geometric object near the comet before the blackout. None of these claims had verification, but the pattern was familiar. The less data there is, the louder the theories become. To astronomers, the missing frames debate illustrates a deeper issue: our dependence on continuity. Space missions like SOHO are built for precision, not drama. When data vanishes, it's rarely malicious, it's mechanical. Radiation spikes, buffer overloads, and telemetry errors are common in high radiation zones near the Sun. Yet in this case, the missing footage aligns too perfectly with the very moment the comet's luminosity surged, creating the illusion of narrative. Independent researchers attempted to cross-check the timeline using data from other instruments: Stereo A, the Solar Orbiter, and Parker Solar Probe. While Parker confirmed a density wave consistent with an energy release, none of the other images had a direct line of sight. The result, one of the most critical astronomical events of the decade, remains visually undocumented. A small team from the Max Planck Institute ran a reconstruction. By analysing the solar wind density patterns before and after the blackout, they inferred a temporary expansion of the comet's plasma envelope. The reconstruction suggests that the brightness surge could have saturated LASCO's CCD array, essentially blinding the instrument. In that case, the blackout wasn't censorship, it was physics. The comet might have literally overwhelmed the camera with light. Still, unanswered questions linger. Why did the auto-safing sequence last 20 minutes instead of the standard 5? Why did internal temperature readings spike only slightly, not enough to justify a complete imaging halt? And why do a handful of frames near the end of the gap show data compression artifacts? Horizontal bands that appear only when telemetry is resynced manually. Conspiracy theories thrive in gaps, but even skeptics admit this one is uncanny. The perfect overlap between the blackout and the burst remains statistically improbable. As one engineer put it, you could record the sun every day for a century and never lose data in a 20-minute window that coincides with a once-in-a-lifetime interstellar event. The missing frames remind us that the frontier of observation is fragile. Sometimes, the greatest mysteries in science aren't hidden by intention. They're lost in the blink of a sensor, erased by photons too powerful to measure. Maybe we didn't lose the data. Maybe we just reached the limit of what our machines can endure. Whatever happened in those missing frames, whether an instrument overload, a perfect coincidence, or something we have no vocabulary for, the silence remains louder than the images themselves. The universe flickered, our cameras looked away, and when they opened again, 3I Atlas was no longer the same. In the hours after the outburst, as scientists pored over spectral data and particle measurements, one detail kept resurfacing: an anomaly in the magnetic readings near the Sun. Instruments aboard both the Solar Dynamics Observatory and the Parker Solar Probe detected a faint but measurable oscillation in the heliospheric magnetic field. The pattern wasn't chaotic. It pulsed at intervals of roughly 9 seconds, sustained for nearly 12 minutes, and then vanished. The signal coincided almost exactly with the window of the 3I Atlas burst. To most, it seemed like background turbulence. To a few, it looked deliberate, a resonance. The Sun's magnetic field is a restless ocean of charged motion. Plasma currents twist and loop through its corona, generating storms that fling energy across millions of kilometers. A comet entering this environment usually acts as a passive object, buffeted and sculpted by the field. But in rare cases, as seen once with Comet NK, The interaction becomes dynamic. The plasma emitted by the comet can couple electromagnetically with the solar field, creating feedback waves. Those waves ripple through space like ripples meeting ripples, amplifying each other when their frequencies align. This is magnetic resonance, the moment two oscillating systems briefly vibrate as one. For 3I Atlas, the alignment appears almost too perfect. The recorded 9-second oscillations match the predicted spin period of the comet's nucleus within a few percent. That means its rotation and the solar magnetic field were momentarily synchronized, at least in terms of frequency. If that alignment allowed energy transfer, the consequences could explain the sudden brightening, not as an explosion, but as induced excitation. Imagine a tuning fork vibrating next to another of the same pitch. Strike one, and the other begins to hum without being touched. In plasma terms, when magnetic fields overlap at resonant frequencies, energy moves efficiently from one system to the other. The sun provides the tone, the comet answers back. For a few minutes, 3I Atlas might have been singing in magnetic harmony with the solar field, absorbing more energy than its surface could safely hold. The result would be an abrupt release of gas and light, the burst we witnessed. The physics behind this isn't speculation. Spacecraft like Voyager and Juno have recorded magnetic resonance effects near planetary magnetospheres. When charged plasma meets oscillating magnetic fields, structures form, standing waves, current sheets, even temporary magnetic mirrors that trap particles. The data from Parker Solar Probe shows just such a mirror forming near the comet's estimated location. A temporary compression of magnetic lines followed by relaxation. It's as if the sun's own magnetic heartbeat briefly skipped a beat. The shape of the outburst supports this idea. The symmetrical shell observed around 3I Atlas could have been a magnetic bubble, a magnetopause formed by resonance pressure. Plasma trapped inside would glow as it cooled, creating the hexagonal structure noted in coronagraph images. Laboratory simulations of plasma bubbles under alternating magnetic fields produce almost identical geometries, with hexagonal cells appearing where currents fold over themselves. But here's where the mystery deepens. Magnetic resonance on this scale requires conductivity, and lots of it. The nucleus of a typical comet is mostly rock and ice, poor conductors by nature. Yet the efficiency of the coupling implies that 3I Atlas possesses regions of high electrical conductivity, perhaps metallic veins or carbon-rich crystalline materials capable of carrying current. That would make it more like a supercooled battery than a snowball. If true, its core composition is far stranger than anything found in our solar system. When scientists mapped the oscillation amplitude, they found another curiosity. The signal phase lagged the sun's field by exactly 1/4 cycle. That's characteristic of inductive coupling, where the secondary system doesn't merely absorb energy but briefly stores and re-emits it. In simpler terms, 3I Atlas didn't just receive the sun's pulse, it sent one back. If resonance truly occurred, it might also explain the faint shockwave Parker detected minutes later. When the coupling broke, when the frequencies slipped out of phase, the stored energy would have dissipated violently, creating a pulse through the surrounding solar wind. That pulse was measured as a localized increase in plasma density, traveling outward from the comet's coordinates. Skeptics caution that correlation doesn't prove causation. Solar plasma is turbulent, and magnetic fluctuations happen constantly. But even they admit the timing is eerie. To have a harmonic oscillation matching the comet's spin, sustained precisely during the burst window and disappearing afterward, is the kind of alignment that keeps astrophysicists awake at night. Whether this was a coincidence, a natural resonance, or something even more complex, one fact remains. The Sun and the interstellar visitor briefly shared a frequency. For 12 minutes, their magnetic fields intertwined, exchanging energy across millions of kilometers. Then the signal faded and silence returned, leaving only the echo of a pattern too precise to dismiss. When the light of the outburst faded and 3I Atlas began its outbound leg away from the Sun, the first assumption was that it had fractured. That would have been logical. A comet under that much thermal and mechanical stress often sheds fragments, small shards of ice and rock that trail behind it like embers from a dying fire. The initial infrared images from the solar orbiter appeared to confirm that scenario. Multiple reflective points moving in close, formation along the object's previous trajectory. The headlines came quickly. Three-Eye Atlas breaks apart near the Sun, but within 48 hours the narrative started to unravel. Those fragments weren't behaving like debris. When a comet splits, its fragments drift apart according to momentum and mass. Smaller pieces move faster, dispersing over time, while larger ones lag behind. The relative spacing increases predictably, forming a faint spreading trail, yet in this case the reflective points didn't drift. They maintained their positions relative to the primary nucleus, moving in perfect geometric alignment, an isosceles configuration that remained stable for more than 20 hours. That's not how debris behaves. It's how orbiting bodies behave. Scientists at the European Space Agency's Operations Centre ran orbital models using the observed positions. The data suggested that the secondary points were gravitationally bound to the primary body, not drifting freely through space. That alone was strange, because a nucleus less than 2 kilometers wide shouldn't have enough gravity to hold on to even meter-scale fragments against solar radiation pressure. Something else was keeping them in formation. One hypothesis proposed magnetic cohesion. If the outburst produced a shell of ionized dust grains, they could be held temporarily by electromagnetic forces clumping together within the comet's plasma tail. Charged particles often behave collectively, forming filaments or sheets that mimic solid structures. This could explain why the debris appeared to rotate synchronously with the nucleus, maintaining fixed distances as though connected by invisible lines. Another more radical suggestion came from radio observations. The Allen Telescope Array, monitoring the region for broadband emissions, detected faint intermittent bursts between 2.8 and 3.1 GHz, the same range used by radar backscatter studies of asteroids. The signal wasn't structured, but it pulsed at intervals matching the nucleus's spin period. The team initially dismissed it as interference, but later analysis showed that the bursts coincided with moments when the reflective points passed behind the comet relative to the observer. In other words, the debris seemed to echo back more strongly when aligned with the nucleus, as if composed of highly reflective material. This raised a provocative question. What were these objects made of? Spectroscopic analysis revealed albedo levels, the fraction of sunlight reflected, significantly higher than any known cometary fragment. Most comet debris reflects less than 5% of incoming light. These points reflected nearly 20%. That brightness is closer to metallic meteorites than to dusty ice chunks. Yet the spectra showed no distinct signatures of iron, nickel or silicates. Instead, they displayed a flat reflectance curve, consistent with highly carbonized material or amorphous composites, perhaps glassy in structure. Some speculated that the debris could be fragments coated in frozen CO2 crystals, temporarily acting as mirrors until sublimation erased the effect. Others wondered if they were not fragments at all but coherent clumps of plasma, magnetic knots shaped by the aftermath of the outburst. Plasma instabilities, such as Birkeland currents, can form self-contained luminous regions that appear solid but are entirely electromagnetic in nature. These structures can persist for hours or even days before dispersing. Still, a small minority of researchers entertained a more exotic possibility. If the geometry remained stable and the reflectivity pattern repeated with mathematical precision, it might suggest structural integrity, the behavior of solid, perhaps engineered objects. To date, no data confirms that. But the symmetry remains hauntingly precise. 3 points forming a perfect triangle rotating with the nucleus at an almost constant angular velocity. Nature can produce order, but rarely with such persistence. By mid-November, the formation began to fade. The secondary reflections dimmed one by one until only the primary nucleus remained visible. Whether they sublimated, dispersed, or simply lost alignment is unknown. The final high-resolution image from the Very Large Telescope showed a faint haze in their place, a cloud of microparticles trailing faintly behind the main body. In official bulletins, the event was catalogued as transient reflective substructures, a deliberately neutral term. But within research circles, it's known by another name, the formation event. Not because it broke apart, but because it seemed to form something, briefly, precisely, and inexplicably, before dissolving back into the void. If those lights were truly fragments, then they broke every rule of motion we know. If they weren't, then they were something far stranger. Remnants of a process we don't yet understand. or perhaps the first visible hint that 3 Atlas's core isn't merely reacting to the Sun, but orchestrating its own behaviour. For now, they remain the unanswered punctuation mark after the comet's burst, debris that isn't debris, geometry that shouldn't exist, and proof that even in the most observed corner of our solar system, mystery still finds space to hide. For weeks after the outburst, scientists struggled to answer a simple question: how dense is 3I Atlas? It should have been a straightforward calculation. Brightness, volume, outgassing rate, and motion under solar radiation pressure all reveal mass. Yet none of the numbers agreed. The comet behaved both heavier and lighter than expected, dense enough to resist acceleration, but porous enough to glow with activity. It was as if it occupied 2 physical states at once, a paradox of mass and motion. Traditional comet models assume densities between 0.3 and 0.6 grams per cubic centimetre, lighter than water, porous like snow. These fragile aggregates of dust and ice fragment easily near the Sun, venting gas that pushes them slightly off course. But 3I Atlas refused to follow those rules. Despite releasing immense amounts of carbon dioxide and dust, its trajectory barely shifted. Calculations of the outgassing thrust showed that if the nucleus were as light as an ordinary comet, the jets should have nudged it measurably. Instead, it held its line. To resist that force, its mass must be higher, perhaps several times greater than expected. Some estimates place its bulk density above 3 grams per cubic centimetre, denser than solid rock. That would make it more akin to a metallic asteroid than a comet. But here lies the contradiction. If it were that dense, its surface gravity should have prevented such violent venting in the first place. The pressure needed to eject CO2 gas at the observed rates would exceed the tensile strength of most rock, and yet the jets erupted freely. So which is it? Lightweight and volatile, or heavy and immovable? Astronomers began examining the problem through indirect clues. The brightness of the coma, the halo of gas and dust surrounding the nucleus, implies how much material escapes per second. Using that rate, and comparing it to the absence of measurable acceleration, scientists derived 2 conflicting answers. Either the nucleus was extraordinarily massive, or the ejected gases somehow cancelled out their own thrust. Both seem implausible, but one must be true. A radical hypothesis emerged from plasma physicists studying the magnetic field interactions. If the comet's jets vent symmetrically in opposing directions, their forces could balance, producing negligible net acceleration. This would require a near-perfect distribution of active vents, a natural impossibility unless the internal structure enforces symmetry. Some suggested that 3I Atlas may possess a core divided into lobes or chambers that release gas in matched pulses, each vent offsetting the thrust of another. The result would be stability without inertia change, a balanced engine effect in nature. Another theory, more controversial, suggests that the nucleus isn't homogeneous at all. Instead, it could contain regions of extremely high density embedded within a porous matrix, dense metallic inclusions locked in a carbon dioxide shell. This would explain both its inertial mass and its responsiveness to solar heating. As the Sun warms the porous regions, gas escapes through weaker zones, while the denser pockets act as anchors, keeping the object's momentum stable. It would also account for the strange rotational deceleration recorded after the outburst. The heavier inclusions could redistribute mass internally, absorbing angular momentum like a gyroscope under stress. Supporting evidence came from polarimetric studies, the measurement of how light scatters off dust. Most comets show predictable polarization curves, but 3I Atlas's pattern was inconsistent. It reflected light as though its dust grains were coated in metallic film, bright at low angles, dark at high. That signature could arise if particles from the interior contained nickel, carbon, or even conductive alloys, materials capable of interacting with magnetic fields. If confirmed, that would mean 3I Atlas is neither a comet nor an asteroid, but a hybrid, a composite body from a system where metallic condensation and volatile accumulation coexisted. Such environments are rare even in our galaxy. They require young, metal-rich stars surrounded by cold, carbon-dense disks. In other words, 3I Atlas may be a relic from an ancient stellar nursery unlike anything in our solar history, a cosmic fossil carrying the architecture of another sun. And yet, the paradox persists. When NASA's trajectory analyst recalculated its mass using the minimal, non-gravitational acceleration, they arrived at a figure implying densities too high to support sublimation at all. By all logic, the comet should be inert, lifeless, but it's not. It breathes, rotates, bursts, and glows. Some researchers now treat the density paradox as a sign that our physical models are incomplete. Perhaps density alone doesn't tell the full story of motion in a charged environment. In the plasma near the Sun, electromagnetic coupling can mimic added mass, allowing an object to resist acceleration without being physically heavy. In essence, the comet could appear massive because it's magnetically anchored to its surrounding field, a plasma body pretending to be stone. Whatever the mechanism, 3I Atlas stands as the first known object to defy the most basic equation in celestial mechanics. Force equals mass times acceleration. The force is measurable, the acceleration is missing. The math doesn't fail often, but when it does, the universe is usually trying to tell us something, and 3I Atlas may be whispering it through the paradox of its own impossible weight. Roughly 10 minutes after the initial outburst of 3I Atlas, radio observatories around the world began to notice something faint, a flicker in the low-frequency spectrum between 20 and 40 megahertz. It wasn't a continuous transmission, nor a natural solar flare. It was a short broadband emission lasting just 32 seconds. The signal rose abruptly, plateaued, and then decayed into the background. Its timing matched the expanding plasma shell seen in optical images almost perfectly. Astronomers quickly realized they weren't listening to radio interference. They were hearing a plasma echo. A plasma echo is one of the rarest phenomena in astrophysics. It occurs when charged particles, electrons and ions, disturbed by an initial event briefly reorganize, storing electromagnetic energy like an elastic field. Then, after a short delay, the system echoes that energy back as a faint secondary wave. It's a kind of memory effect, the plasma equivalent of a room ringing after a bell stops. Plasma physics predicts it, but it's seldom observed outside of controlled experiments. Seeing one in interplanetary space is almost unheard of. The first reports came from the Owens Valley Radio Observatory in California. They were tracking solar background noise when the instruments picked up an unusual harmonic sequence. Multiple frequency peaks spaced evenly apart, as though the plasma itself were oscillating like a struck string. Within minutes, confirmations came from stations in Chile, South Africa, and Japan. All recorded the same frequency pattern, though each with slightly different intensity depending on their angle to the Sun. When the data were combined, the triangulation pointed precisely to one origin, the coordinates of 3I Atlas, at the moment it reappeared from behind the Sun. The emission's spectral fingerprint ruled out ordinary solar causes. Solar flares and coronal bursts produce chaotic, broadband static. This signal, though brief, was structured, clean, repeating, and fading with a mathematical decay curve consistent with damped plasma oscillations. It suggested that something in or around the comet had absorbed energy from the CME, held it briefly, and then released it back into space as an electromagnetic pulse. That possibility fascinated physicists. If 3I Atlas's coma, composed mostly of carbon dioxide ions, acted as a resonant cavity, it might have temporarily trapped the CME's charged particles. When the field relaxed, the trapped electrons could have oscillated collectively, producing the observed echo. In laboratory plasma chambers, this effect can be triggered when dense ion clouds meet oscillating magnetic fields. The resulting emission carries the memory of the initial disturbance, literally an electromagnetic echo of the impact. The brightness of the signal, however, posed a problem. For it to be detected across half the planet, the plasma density had to be far higher than previously estimated. That implies the coma was denser, thicker, and more conductive than any typical cometary gas cloud. Some scientists proposed that the plasma had temporarily condensed into a quasi-solid state, a magnetized envelope of ionized carbon dioxide strong enough to store and release energy like a capacitor. The shape of the waveform deepened the mystery. It contained 3 distinct peaks separated by equal time intervals, a triple pulse echo. In physics, that pattern indicates structured geometry in the emitting region. Each pulse likely corresponded to energy rebounding between concentric layers of plasma, as though the object's atmosphere had stratified into shells. That would fit the earlier observations of a hexagonal expansion during the outburst. The plasma didn't just disperse, it resonated in layers, humming before it faded. No one could recall another interstellar visitor doing anything remotely similar. Even Comet Borisov, which showed unusually high activity, never produced a detectable radio echo. This made 3I Atlas the first interstellar object to exhibit post-event plasma resonance, an entirely new behavior class. A team at MIT's Haystack Observatory processed the full spectrum and converted it into an audible sound. What emerged was haunting, a deep, rising tone followed by 3 quick descending pulses, almost like a sonar ping reflected through water. For outreach purposes, they dubbed it the Voice of Atlas. While poetic, the term isn't far from reality. The plasma echo was literally the object's electromagnetic voice, the aftersound of an energy exchange between an interstellar body and our Sun. It provided the first direct evidence that 3I Atlas isn't just reacting chemically to solar radiation, but electromagnetically to solar plasma. For astrophysicists, that's monumental. It suggests that interstellar objects might not be passive stones travelling through the solar system, but active participants in its plasma environment, amplifying, absorbing, and even replaying the Sun's signals. The signal ended as abruptly as it began, fading into the ordinary radio hiss of the solar wind. But it left behind a fingerprint, 3 harmonic peaks in perfect ratio, etched into radio archives across the globe. In them lies the echo of a moment when the Sun and a visitor from another star system briefly spoke the same electromagnetic language, and for 32 seconds the universe answered back. It began as a footnote, a small irregularity buried deep within a stack of magnetometer readings from NASA's Messenger Data Archive and ESA's Bepi-Colombo mission logs. On the day 3I Atlas burst near the Sun, Mercury's magnetic field recorded a faint transient spike lasting just over 90 seconds. It was so small it barely rose above the noise threshold. But when researchers synchronized the timestamps with heliocentric coordinates, the anomaly matched the exact moment of the comet's plasma outburst. The implication was almost absurd. Mercury, 58 million kilometers away, had flinched. Mercury's magnetic field, though weak, is highly sensitive to solar disturbances. The planet sits in one of the harshest electromagnetic environments in the solar system, bathed in solar wind, exposed to constant radiation, and surrounded by a magnetosphere that fluctuates like a heartbeat. Every CME, flare, and plasma surge from the Sun leaves a signature. But this signal was different. It wasn't consistent with a coronal mass ejection or solar flare impact. The data showed a downward dip in magnetic intensity, followed by a rebound, as though a passing shadow had briefly distorted the field. Scientists call such events magnetospheric depressions. They occur when plasma density near a planet suddenly increases, compressing the magnetic lines inward. Normally, that compression follows the impact of a solar wind shock, yet no such shock was recorded that day. The solar wind speed remained steady, its density unremarkable. The only event capable of causing a temporary electromagnetic fluctuation in that region was 3I Atlas, the same interstellar visitor that had erupted minutes earlier near the Sun's southern hemisphere. The connection seemed impossible at first. The comet was nowhere near Mercury's orbit. Their separation was vast. But when researchers modelled the propagation of the CME that struck 3I Atlas, they found that the shockwave's secondary field lines could have stretched toward Mercury's magnetosphere, carrying remnants of the interaction. In essence, when the CME hit the comet, it generated a localized distortion, a ripple, that radiated outward through the solar plasma. Mercury, positioned almost directly along that field line, could have received the echo. It's not the first time a celestial interaction has cast an electromagnetic shadow. During intense solar storms, Earth's magnetosphere occasionally records similar delayed ripples caused by CME reflections off planetary bow shocks or dense plasma structures. But this would be the first instance linked to a single, transient interstellar object. The ripple's arrival, 90 seconds after the 3I Atlas burst, fits almost perfectly with modelled transit speeds of magnetic waves in that region of the heliosphere, about 500 kilometers per second. Still, there was something else, a visual trace. Bepi-Colombo's ultraviolet spectrometer, facing the Sun at that moment, captured a brief darkening in scattered solar light. For 3 consecutive frames, just over a minute of exposure, The sensor registered a narrow linear drop in intensity across Mercury's dayside limb. It wasn't an eclipse or an instrumental glitch. The darkening moved too fast and disappeared too cleanly. It looked, quite literally, like a shadow sweeping across the planet's atmosphere, though Mercury has no atmosphere thick enough to project or receive such a thing. The prevailing theory is that the darkening wasn't optical but electromagnetic. When high-density plasma crosses a magnetic field, it can refract radio and ultraviolet waves, creating localized absorption zones. In this sense, Mercury's shadow wasn't cast by light but by magnetism, a fleeting distortion caused by the same plasma wave that registered on the magnetometer. The comet's burst had sent an invisible pulse through the Sun's lower corona, and Mercury briefly wore its imprint. To planetary scientists, the implications are fascinating. It suggests that even small, transient events in the inner solar system can create detectable electromagnetic reverberations across planetary orbits, the space equivalent of thunder rolling after lightning. 3I Atlas's eruption wasn't just a local event near the Sun, it was a system-wide tremor. The shadow that touched Mercury may have been the first measurable sign of how energy transfers between interstellar matter and solar plasma on a planetary scale. When the data was presented to the European Planetary Science Congress, reactions were mixed. Some dismissed it as coincidence, a background fluctuation exaggerated by timing. Others, including the magnetosphere team at ESA, argued that the probability of such a synchronized event occurring randomly was less than 1 in 10,000. They called it the magnetic handshake, a poetic term for an event that technically defied definition. In the final analysis, nothing visible remains. No crater, no trace, no residue. Just a blip in Mercury's magnetic memory, a whisper in ultraviolet light, and a timestamp that aligns too neatly to ignore. For 90 seconds on October 29th, a planet closest to the Sun may have momentarily felt the breath of an interstellar traveller, a shadow not of matter, but of resonance, passing silently across its magnetic skin. When 3I Atlas emerged from behind the Sun, the world expected fireworks. Astronomers had braced for a luminous spectacle, the bright, ragged tail of an object that had just survived its closest pass to the star. Every known comet that endures perihelion shines intensely afterward, its volatile ices superheated, its coma expanding. But when the cameras turned back toward the coordinates on October 30th, what they found was absence. The object was there, faintly visible, but muted, quiet, stripped of its brilliance. The once blazing traveller that had outshone predictions by orders of magnitude just hours earlier now glowed like a distant ember. This moment became known as the optical silence. In astronomy, silence doesn't mean nothing is happening, it means whatever is happening we can't see it. The dimming of 3I Atlas wasn't gradual, it was abrupt. Within a span of a few hours, its visual magnitude dropped by nearly 50%. Such rapid fading implies one of two possibilities: catastrophic disintegration or complete stabilization, yet neither fit the available data. The comet's structural light curve remained steady, no tumbling, no rapid shape changes, and radar pings from deep space antennas confirmed the presence of a solid nucleus. It hadn't exploded or vanished. It had gone dark. This contradicted everything astronomers knew about post-perihelion behavior. After a burst of energy, residual heat usually drives secondary venting. Gas escapes through newly opened fissures, increasing reflectivity as sunlight scatters off the fine dust. But 3I Atlas displayed none of that. The dust trail that should have brightened was thin, uniform, and strangely static, like an old contrail fading in still air. The simplest explanation was exhaustion, that the comet had vented most of its volatiles during the outburst and was now inert. But spectral readings told a different story. Infrared instruments continued to detect faint carbon dioxide emissions, meaning activity persisted, just not visibly. The gases escaping weren't carrying dust, they were escaping cleanly. That's unusual, because dust particles are what make comets visible. Without them, the gas is transparent to optical light. The result is an active body that shines only in infrared and radio wavelengths, a comet we can't see but can still measure. Some researchers described it as self-shadowing. The theory goes that the outburst near perihelion left a layer of fused carbon on the surface, a thin, glassy crust created when CO2 ice sublimated violently and recondensed as carbon residue. That crust, black and non-reflective, would absorb sunlight instead of scattering it, turning the nucleus into a matte object, invisible in the optical spectrum but alive underneath. Laboratory tests of carbon sublimate residues support this. Under intense heat, CO2-rich dust can fuse into amorphous carbon films with near-zero albedo. Others proposed electromagnetic causes. During the burst, 3I Atlas interacted directly with the Sun's magnetic field. If the surface accumulated electric charge, it might have rearranged dust grains into a cohesive layer, a process called electrostatic sintering. Such a layer could seal vents and alter reflectivity without halting sublimation beneath. In that case, the comet wasn't inert, it was cocooned, a blackened shell trapping volatile gases within. Optical silence, then, wasn't absence but transition, the aftermath of a body entering a new thermal equilibrium. The light it once reflected now radiated at longer wavelengths, invisible to our eyes but detectable to machines. Indeed, when the James Webb Space Telescope turned its infrared sensors toward the object days later, it found it glowing brightly in those longer bands. 3I Atlas hadn't died. It had changed the language of its light. Still, the psychological effect of that silence rippled through the astronomical community. For weeks, the comet had been a media spectacle, the bursting visitor, the green interstellar messenger. And then, silence. No tail, no colour, just darkness. In a way, it was poetic. An alien traveller refusing to perform for our eyes, reminding humanity that visibility isn't the same as presence. Some analysts compared it to the optical blackout seen in plasma discharges, where ionized gases suddenly transition to non-luminous states when electrical balance is restored. If the burst was an electrical event, a magnetic resonance or discharge, then the fading light could represent the system stabilizing. The comet, in effect, had returned to equilibrium, its plasma shell neutralized. By November 2nd, 3 Atlas's brightness had stabilized at magnitude 13, too dim for most amateur telescopes, but infrared sensors continued to pick up emissions weeks later, suggesting that whatever powered its activity now operated in silence. For scientists, this was the moment. 3I Atlas ceased to be a spectacle and became a mystery. Its optical silence was not an ending but a threshold, the point where light, matter and magnetism merged into something our eyes could no longer register. It's rare in science to witness the universe turning down its volume so deliberately. One day, its light spoke in flares and geometry. The next, it whispered only in heat. And somewhere, beyond the sun's glare, 3C Atlas continued its journey, invisible, intact, and still very much alive. When 3I Atlas finally reappeared from solar conjunction, ground-based observatories noted something subtle but extraordinary. Its brightness profile didn't just dim, it changed character. The way it reflected light was different. Photometric analysis showed that the comet's albedo, its ability to reflect sunlight, had increased by nearly 20%, even as its overall luminosity decreased. In plain terms, it was reflecting light more efficiently, but from a smaller or altered surface. Astronomers called this phenomenon the reflectivity shift. At first, this seemed contradictory. A body growing dimmer yet becoming more reflective shouldn't be possible unless its geometry, composition, or surface texture had changed dramatically. But that's precisely what many now believe happened during the perihelion burst. The violent expansion near the Sun likely stripped away layers of dark, carbon-rich material that had coated the comet for eons, exposing fresh subsurface ice or crystalline minerals beneath. That new surface, smoother and more uniform, scattered sunlight differently, cleaner, whiter, more directional. Comets are usually among the darkest objects in the solar system. Their surfaces, baked and bombarded by radiation over millennia, become coated in tar-like organics known as tholins. These compounds absorb most visible light, making comets appear almost black despite their glowing comas. When such material is suddenly ejected or vaporized, the underlying ice reflects light much more effectively. For 3I Atlas, the shift in reflectivity may mark the moment its interstellar skin peeled away, a literal resurfacing of an alien worldlet. Spectroscopic evidence supports this idea. instruments from the Very Large Telescope in Chile detected a change in polarization, the orientation of reflected light waves, immediately after the burst. Before perihelion, the reflected light showed a high degree of negative polarization, typical of dark, porous surfaces. Afterward, the polarization reversed, a sign that light was now scattering off smoother, more crystalline material. This switch is rare and almost always indicates exposure of unweathered terrain. The physical mechanism behind that exposure remains debated. One camp argues that the sun's heat alone vaporized the upper layers, much like ice turning to gas. Another believes the real driver was mechanical, that the internal gas pressure during the burst blasted away the insulating crust, revealing fresh ice and mineral deposits. If the latter is true, 3I Atlas effectively shed its outer coat like an ablating spacecraft. For a few brief hours, its true surface, untouched since it left its home system, glimmered in solar light for the first time. There's another layer to this mystery, the spectral colour. Pre-burst, 3I Atlas exhibited a greenish hue typical of carbon-based gas emissions. Post-burst, its colour balance shifted toward neutral white. The green glow didn't vanish entirely but dulled dramatically, as if the source gases had been depleted or shielded. In its place, reflectivity increased most strongly in near-infrared wavelengths, a range consistent with silicate minerals or icy grains coated in thin frost. Some researchers proposed that sublimated gas recondensed as frost on the shadowed sides of the nucleus, temporarily boosting reflectivity in those regions. Others suggested that electrostatic charging caused dust particles to realign, smoothing the surface and reducing its roughness on a microscopic scale, a natural polishing effect in vacuum conditions. But perhaps the most intriguing observation came from the European Southern Observatory's photometric phase curves. They showed that 3I Atlas's brightness now varied with solar angle more sharply than before, a telltale trait of specular reflection, where light bounces off a surface in a preferred direction rather than scattering diffusely. In other words, it began to reflect like metal, not dust. No comet has ever displayed such optical coherence. The implication is startling. Either the burst created smooth, glass-like ice layers capable of mirror-like reflection, or it uncovered naturally reflective strata buried beneath centuries of dark insulation. The reflectivity shift also changed the comet's apparent texture in high-resolution imagery. Before perihelion, its coma appeared grainy, filled with diffuse dust. Afterward, the coma thinned, and the nucleus's sharp edges became more defined. Another hint that dust production dropped while surface brightness per unit area increased. The comet was no longer cloaked in haze but gleaming, bare and angular. Some physicists went further, speculating that the reflectivity might not come solely from physical matter, but from electromagnetic phenomena. When plasma interacts with charged dust near a magnetic boundary, it can create transient reflective layers, plasma mirrors, that bend or enhance light briefly. If 3I Atlas's surface retained a residual electromagnetic field from its resonance with the Sun, the glow we see might partly be an optical illusion, sunlight refracted through electrically charged gas. Whatever the mechanism, the reflectivity shift marked a clear transformation. The comet that entered perihelion was dark, organic and turbulent. The one that emerged was clean, crystalline and calm, as though something had scrubbed it of its history. Astronomers likened it to the way a gemstone looks when freshly cut. Rough edges gone, internal structure exposed. For a visitor from another star, this transformation feels almost poetic. 3I Atlas journeyed for millions of years wrapped in the soot of its creation, only to shed that cloak in a single moment of light. What we now see may not be the comet as it was, but as it truly is, a mirror not just of sunlight, but of the hidden clarity that sometimes follows the storm. When the solar orbiter transmitted its latest batch of high-resolution images back to Earth, analysts noticed something astonishing buried within the data: a spiral-shaped plume extending thousands of kilometers outward from 3I Atlas. It wasn't the chaotic tail of dust one might expect from a typical cometary eruption. This was structured, coherent, and rhythmic. The jet twisted outward in a precise helical pattern, like smoke curling in slow motion through a vacuum. For the first time, astronomers were witnessing what they later called a spiral jet, a rotating filament of plasma and gas that seemed to pulse, in synchronization, with the comet's own spin. At first, the spiral was faint, only visible through image enhancement. But once isolated from the surrounding glare of the sun, its geometry became unmistakable. The plume unfurled like a corkscrew, maintaining a consistent pitch angle across multiple frames. That regularity alone ruled out random venting. Ordinary comets eject gas in short, uneven bursts. The result is chaotic turbulence, not order. This, by contrast, was almost mechanical in precision. Every rotation of the nucleus appeared to produce one complete turn of the spiral, implying that the jet source remained active on a fixed point of the surface, a stable vent or fissure that rotated with the body. The idea of a single vent producing such a vast, continuous structure defied expectation. Most cometary outflows collapse under their own expansion, but this one persisted, as if shaped by an invisible guide. Plasma physicists proposed that the spiral could be magnetically constrained. As the charged gases left the surface, they might have followed the lines of the comet's induced magnetic field, a field generated as the conductive CO2-rich material interacted with the solar wind. The combination of rotation, ionization, and magnetic tension would naturally create a corkscrew configuration. To test that idea, scientists modelled the event using magnetohydrodynamic simulations. The results were eerily accurate. A rotating body with even a weak internal magnetic moment could produce a spiral jet if its outgassing rate and solar wind conditions aligned perfectly. The model also predicted something else. The spiral should carry distinct layers of charge, positive ions on the outer edge, electrons near the core. Such charge separation would cause the structure to glow unevenly, creating a faint pulsing brightness. And indeed, time-lapse. Observations from the stereo spacecraft showed the jet flickering rhythmically every 8.6 seconds, exactly the nucleus's measured rotation period. But there was more to the spiral than its beauty. Embedded within its coils were microfilaments of dust that appeared to follow the plasma lines, forming thin, luminous strands visible in polarized light. Each filament oscillated slightly, as if vibrating under tension. This subtle movement could represent Alfvén waves, ripples in the magnetic field travelling along the plasma spiral. Detecting Alfvén waves in such a small-scale environment is rare. They're typically associated with the Sun's corona or planetary magnetospheres, not comets. The fact that 3I Atlas produced them suggests a level of electromagnetic interaction far beyond the norm for small icy bodies. Spectral analysis of the jet revealed another surprise. Instead of water or hydroxyl emission lines, the spiral displayed enhanced carbon and oxygen ionization bands, evidence that the jet's gas was pure carbon dioxide plasma. The absence of neutral molecules means the ejected material had been stripped of electrons almost immediately upon release. In other words, the spiral wasn't just a stream of gas, it was electrically alive. As the days passed, the spiral expanded and gradually dissipated, stretching tens of thousands of kilometers into the surrounding solar wind before fading completely. Yet its legacy remained in the data. It proved that 3I Atlas could channel its energy not chaotically, but rhythmically, as though governed by internal order. The fact that such a coherent plasma structure could form around an interstellar object raises profound questions about its composition. Does it possess a conductive core? Is there a magnetic lattice beneath its crust? Could the spiral jet represent not randomness, but resonance, a natural alignment between the comet's rotation and the Sun's electromagnetic field? In one of the final reports, a researcher described the jet as a thread stitched through sunlight. The phrase captured the sentiment shared across observatories worldwide, or mixed with confusion, because if this spiral truly arose from natural processes, it means interstellar comets are capable of electromagnetic behaviors we've never observed locally. And if it didn't, if the symmetry was too perfect, the pattern too deliberate, then 3I Atlas isn't just a visitor, it's a demonstration, a cosmic mechanism revealing that, even in the heart of chaos, geometry persists. For now, all that remains is the data, the rotating nucleus, the pulsing jet, the spiral pattern winding outward into darkness. A motion written into plasma, as if 3I Atlas was spinning not just in space, but in rhythm with something larger, invisible and ancient. A silent dance between magnetic fields that only the universe itself could choreograph. When the Parker Solar Probe transmitted its data back to Earth 2 days after 3I Atlas's perihelion burst, mission analysts noticed an anomaly in the solar wind readings, a sudden spike in plasma density and magnetic compression, followed by a brief, symmetrical dip. It lasted less than 40 seconds. The waveform looked familiar, but the source didn't fit. It wasn't a coronal mass ejection, nor a flare-driven shock. The sun itself had been quiet. The signal appeared to radiate away from the comet's position, as if the interstellar visitor had generated a shockwave of its own. Shockwaves in space are delicate things. Without air or solid matter, they exist not as sound but as waves of pressure and magnetism rippling through plasma, disturbances that travel faster than the local speed of Alphen waves, compressing charged particles into a sharp front. They're born from violence, solar eruptions, planetary magnetospheres, or exploding stars. A comet, by contrast, is too small and too fragile to create one, yet the data was irrefutable. At 1446 UTC, moments after the outburst, Parker's magnetometer registered a sudden 18% increase in magnetic field strength and a 5-fold rise in proton density, a textbook signature of a passing shock front. The timing lined up perfectly with the outburst recorded by the Solar and Heliospheric Observatory. The direction vector pointed precisely back to the coordinates of 3I Atlas. Whatever had happened there, it had sent a pulse, a wave that propagated outward through the solar plasma at nearly 600 kilometers per second. That's not a random fluctuation, that's an explosion. But how does a comet create a shock wave without disintegrating? The leading theory focuses on plasma interaction. When the coronal mass ejection slammed into 3I Atlas, the impact ionized vast quantities of carbon dioxide gas surrounding the nucleus, transforming it into a temporary magnetized cloud. That cloud, expanding rapidly into the solar wind, created a discontinuity, a boundary where density, temperature, and magnetic pressure changed abruptly. The result, a self-propagating magnetic shock. To visualize it, imagine dropping a pebble into a calm pond, but instead of water, the pond is made of invisible plasma currents. The ripple travels outward, carrying energy and information about the impact. In this case, the pebble wasn't physical. It was electromagnetic, the sudden coupling of the comet's ionized envelope with the sun's magnetic field. For a brief moment, 3I Atlas and the solar wind were one system, and the energy they exchanged rippled through the heliosphere. Interestingly, this isn't without precedent. In 2007, when a CME struck Comet NK, the interaction produced a disconnection event. The comet's plasma tail was ripped off, forming a visible kink in the solar wind. But the 3I Atlas event was orders of magnitude stronger. No disconnection occurred. Instead, a symmetrical compression wave expanded around it like a bubble, detected not only by Parker but also by solar orbiter instruments trailing millions of kilometers away. 2 spacecraft, 2 different vantage points, 1 shared pulse. This wave carried consequences. The local solar wind slowed by nearly 5% for several minutes, as though dragged backward by the compression. Then it rebounded, accelerating again. That rebound produced faint oscillations, echoes of the main event, that persisted for hours. For heliophysicists, it was a rare natural experiment, an object from another star acting like a miniature magnetized engine inside our solar system, generating a coherent wavefront strong enough to alter the ambient solar environment. And yet, the energy required to do this remains unexplained. Based on Parker's readings, the total energy of the shockwave was equivalent to roughly 10-15 joules, comparable to a small terrestrial earthquake. That's impossible for a kilometre-wide comet driven only by sunlight and gas expansion. Some researchers suspect magnetic resonance amplification, that the CME's field and the comet's induced field briefly aligned, magnifying the effect exponentially before snapping apart. When the alignment collapsed, the stored magnetic tension released instantaneously, creating the pulse Parker recorded. The comet itself seemed unscathed. When visual data resumed, 3I Atlas remained intact, spinning calmly, its coma reshaped but whole. It had absorbed a storm, released a wave, and survived. That resilience defies physics as we know it. If the shockwave was purely mechanical, it should have fractured the nucleus. But if it was magnetic, the pressure could have passed through without damage, like a resonance that shakes space but not matter. For days afterward, the wave continued to drift outward, detectable in the solar wind as a faint ripple of increased density. By the time it reached Mars's orbit, it had dissipated into noise, but deep in the data archives its fingerprint remains, a perfect symmetrical pulse born from a traveller that shouldn't have been able to make one. To the scientists who studied it, this was more than a curiosity. It was a warning, a sign that interstellar bodies may not behave passively in stellar environments. Under the right conditions, they might interact energetically, even violently, shaping the space around them. 3I Atlas's shockwave wasn't just a byproduct of physics. It was a statement, proof that the sun itself can be momentarily echoed by a visitor from another star. When astronomers first traced the dust trail of 3I Atlas after its perihelion burst, they expected a familiar picture, a diffuse fan-shaped plume stretching away from the sun, gradually curving under the pressure of solar radiation. That's how comets behave. The sun pushes on their dust, bending it outward like wind through smoke. But what appeared in the deep field imagery from the solar orbiter and Earth-based telescopes defied that pattern entirely. The trail wasn't curved in the expected direction. It arced against the solar wind, a reverse sweep. At first, researchers assumed an error in the processing pipeline. Instruments sometimes misregister angles when filtering out background stars, yet independent observations from Chile, Spain and Japan confirmed the same anomaly. The dust tail of 3I Atlas wasn't following the photonic path dictated by sunlight. It was shaped by something else. To understand why this was so astonishing, it helps to recall what controls a comet's tail. The dust component, composed of microscopic rock and carbon particles, responds primarily to light pressure and the sun's gravity. The ion tail, made of charged gas, reacts instead to magnetic fields carried by the solar wind. These two tails usually point in slightly different directions, but both extend away from the sun. 3I Atlas, however, seemed to defy both categories. Its trail bent laterally, not radially, as though drawn along invisible arcs. Using high-contrast imaging, analysts discovered that the dust wasn't dispersing randomly. It was forming layers, faint striations stacked like ripples on water. Each layer represented particles of a specific size and charge. The smaller, lighter grains should have accelerated faster, but instead they clumped into linear filaments, maintaining rigid spacing. When plotted in 3 dimensions, those filaments formed a twisting ribbon, a helix coiling gently behind the nucleus. It was the same geometry seen earlier in the spiral jet, replicated on a grander scale. This revelation led to a startling hypothesis. 3I Atlas's dust trail was magnetically organized. The plasma environment surrounding the comet may have imprinted its internal field pattern onto the escaping particles, arranging them into ordered filaments rather than scattering them chaotically. If true, this would make 3I Atlas not merely reactive to the solar magnetic field, but capable of shaping it, however briefly, through induced magnetism. To test this, researchers at the European Space Astronomy Centre ran simulations combining plasma dynamics and radiation pressure. The results were uncanny. If the comet possessed even a weak residual magnetic moment, just 1/10,000th that of Earth, its interaction with the solar wind could create magnetic streamlines that trapped charged dust along curved paths. Those streamlines would bend in precisely the direction observed, opposite the solar radiation flow, with slight rotation around the comet's trajectory. Spectroscopic measurements added another clue. The dust grains emitted polarized light that oscillated at frequencies consistent with magnetic alignment, similar to how iron filings line up along a bar magnet. But the grains themselves were non-metallic, carbonaceous, and silicate-based. That suggested the alignment wasn't intrinsic to the particles, but induced by external, electromagnetic fields. For a short window after the burst, 3I Atlas's environment may have acted like a magnetized bubble, choreographing every particle that escaped it. Another intriguing aspect was the trail's persistence. Typical dust tails diffuse quickly as particles disperse along orbital paths, yet this one remained sharply defined for days. The inner structure, the double helix pattern, didn't unravel even after hundreds of thousands of kilometers of travel. That coherence implies that magnetic tension or electrostatic cohesion held it together, counteracting the sun's dispersive forces. In effect, the trail behaved more like a plasma filament than a simple stream of inert dust. Observers compared it to Birkeland currents. the vast twisted filaments of plasma that connect planets and stars across space. On a microcosmic scale, 3I Atlas appeared to have generated its own. If so, this may have been the first direct evidence of interstellar material producing self-organized electromagnetic structures within the heliosphere. The dust wasn't just debris, it was a physical map of invisible forces. By the time it reached 0.5 astronomical units from the Sun, the geometry began to dissolve. The magnetic coherence faded, the filaments frayed, and the trail adopted a more conventional shape. But by then, the data had already been captured. The European Southern Observatory's images revealed a pattern so mathematically precise that astrophysicists described it as engineered by nature. For now, the consensus remains cautious. Official bulletins refer to the phenomena as anisotropic dust dispersion under transient magnetic influence. But among those who witnessed the raw data, a quieter idea circulates, that 3I Atlas, for a brief moment, demonstrated how even dust can obey order when guided by electromagnetic harmony. The trail wasn't merely residue from an outburst, it was choreography, geometry written in carbon and light, spiraling through space like the faint signature of intelligence in motion. One of the most puzzling discoveries in the aftermath of 3I Atlas's solar encounter came not from what telescopes saw, but from what they measured, the sudden change in the object's spin. Before perihelion, the comet's rotation period was precisely catalogued at 8.6 seconds per photometric pulse. After the burst, that period stretched to nearly 9.7 seconds, a drop of over 12%. For an interstellar object only a kilometre wide, such a dramatic rotational slowdown in mere hours borders on the impossible. Yet the data, collected independently by observatories in Chile, Japan and Spain, all said the same thing. 3I Atlas had lost angular momentum. Comets do change their spin rates, but slowly and for predictable reasons. When jets of gas escape a rotating body, they act like tiny thrusters, speeding it up or slowing it down depending on their orientation. For example, Comet 67P Churyumov-Gerasimenko, studied by ESA's Rosetta mission, altered its spin by a few minutes over several months due to outgassing. But a 12% reduction in rotation over a single day? That's orders of magnitude beyond any known mechanism. Something far more powerful, or far stranger, had acted on 3I Atlas. The leading explanation centres on symmetry. The outburst near the Sun wasn't random venting, but a near-simultaneous release of gas and dust across multiple surface fissures. If those jets erupted opposite the direction of spin, they could have counteracted the object's angular momentum, yet the energy required to produce such braking would have been colossal, the equivalent of detonating several megatons of TNT in synchronized opposition to the spin vector. For a fragile cometary nucleus, such an event should have shattered it. But 3I Atlas remained intact, almost serene in its post-burst trajectory. This raised a disturbing possibility. Perhaps the slowdown wasn't caused by physical jets at all. Researchers turned to magnetic modelling. During the burst, 3I Atlas interacted directly with the Sun's magnetized plasma. If its body possessed conductive materials, metallic inclusions or carbon lattices capable of carrying current, it could have experienced electromagnetic drag. In physics, this is known as Lorentz braking. When a conductive object moves through a magnetic field, eddy currents are induced, generating forces that oppose motion. On Earth, the same principle is used in magnetic braking systems for trains. In space, under the right plasma conditions, it could decelerate rotation without physical contact. The theory gained traction when Parker Solar Probe data revealed an abrupt change in magnetic flux density precisely during the spin drop. The field around the comet fluctuated, then stabilized at a higher alignment angle, a textbook signature of induced current. If 3I Atlas's coma briefly functioned as a conductive envelope, interacting with the Sun's magnetic field, it might have converted rotational energy directly into heat, or electromagnetic radiation. In other words, it could have bled angular momentum into space. Further evidence came from the infrared spectrum. Post-burst, the comet's temperature fell faster than expected, implying a sudden loss of internal energy. That could mean the slowdown wasn't purely mechanical, but also thermal, a redistribution of energy from motion into heat. If the comet's crust contained alternating conductive and insulating layers, a massive current pulse could have formed eddy vortices, effectively braking the rotation while diffusing the excess energy through its outer shell. Still, even this explanation fails to capture the precision of the change. The slowdown wasn't erratic, it was clean. The light curve shows a smooth, continuous deceleration over roughly 30 minutes before stabilizing at its new period. No tumbling, no precession, no signs of fragmentation. It was as if the comet had deliberately eased its spin to a lower equilibrium state. This level of stability intrigued dynamicists. Some noted that the new rotation rate aligned almost exactly with the Sun's local magnetic oscillation frequency at that region of the heliosphere. Coincidence? Perhaps, but the match was too exact to ignore. It suggested that 3I Atlas might have reached a resonant lock, synchronizing its rotation with surrounding plasma waves, the way a pendulum matches the rhythm of the force driving it. If true, this would be the first recorded instance of an interstellar body achieving magnetic rotational coupling with the Sun. In simple terms, it would mean the comet temporarily listened to the Sun's field, adjusted, stabilized, and settled into rhythm with it. Skeptics argue the event could still be coincidence, the product of rare but natural feedback between outgassing and shape asymmetry. Yet even they concede that no known comet has ever decelerated so rapidly, so evenly, and survived intact. To this day, the rotation drop stands as one of the most elegant riddles in 3I Atlas's story, a moment where physics bent but didn't break, where a fragment of another star system seemed to sense our Sun's pulse and respond in kind. Whether it was magnetic drag, synchronized resonance, or something we have no language for yet, one truth is clear. 3I Atlas didn't just spin, it listened. And then, for reasons unknown, it slowed down to match the rhythm of a universe it had never called home. When the post-perihelion spectra of 3I Atlas were first compiled, astronomers expected a familiar chemical fingerprint, strong emission lines from hydrogen, oxygen, and hydroxyl radicals. These are the hallmarks of water, the dominant volatile in most comets. But when the data came in, one line was missing. The hydrogen Lyman alpha band, which always flares near the Sun as water vapor breaks apart, was silent. Not weak, not obscured, simply gone. At first, the emission was written off as instrument error. Maybe the detectors were saturated by the Sun's glare, or perhaps the comet's geometry prevented clear observation. But follow-up readings from the Solar Orbiter, the Parker Solar Probe, and even the Hubble Space Telescope confirmed the same pattern. Every expected molecular signature of water was absent. In its place were dominant bands of carbon dioxide, oxygen ions, and a faint trace of molecular nitrogen. 3I Atlas, it seemed, carried almost no hydrogen at all. This finding is more than a chemical curiosity, it's a clue to origin. In our solar system, comets are primordial water reservoirs. They formed in the cold outer regions where hydrogen and oxygen combined easily into ice. But hydrogen is fragile, it escapes quickly in warm, young stellar systems. For an interstellar comet to arrive here without any hydrogen means it either formed in a radically different environment, or underwent processes that stripped it completely. Astrophysicists proposed two main theories. The first, 3I Atlas, was born in a system where hydrogen never dominated, perhaps around a star rich in carbon, but poor in volatiles, such as a red dwarf with a depleted protoplanetary disk. In that case, its ices would be carbon dioxide, methane, and nitrogen-based, not water-based. Such chemistry would make it denser, darker, and more stable near stars, consistent with its behavior near our Sun. The second theory is more exotic. Some suggest that 3I Atlas once carried water, but lost it through ion stripping during interstellar travel. Between stars, radiation from cosmic rays and plasma shocks can gradually erode lighter elements. Over millions of years, hydrogen atoms can be sputtered away, leaving behind heavier oxides and carbonates. The object that entered our solar system, then, may be the mineralized core of a once icy body, a fossil stripped of its most common element. Yet even this doesn't fully explain what scientists observed. The comet's coma, the glowing envelope surrounding the nucleus, was unusually bright in oxygen emissions. If water wasn't the source, where was the oxygen coming from? Some hypothesize that superoxides or peroxides embedded in the crust were breaking apart under solar heat, releasing O2 directly without hydrogen. Others proposed a new process altogether, high-energy photon bombardment dissociating trapped carbon dioxide. creating oxygen plasma independent of hydrogen chemistry. That mechanism would make 3I Atlas's outburst less a thermal event and more an electrical one, a burst driven by charge separation rather than evaporation. It aligns with the plasma behaviors observed during the burst, including the magnetic resonance and shockwave phenomena. Without hydrogen, the lightest and most mobile element, charge equilibrium would behave differently. The object could build immense electrostatic potential before discharging catastrophically. In that sense, the missing hydrogen may not just be a chemical footnote, it may have shaped the entire sequence of anomalies we witnessed. The absence also carries cosmological implications. Hydrogen is the most abundant element in the universe, making up roughly 70% of all baryonic matter. Finding a body completely devoid of it is like finding a melody without its fundamental note. It challenges the assumption that interstellar debris is compositionally universal. If 3I Atlas truly lacks hydrogen, it might represent matter forged in an environment where typical hydrogen chemistry never occurred, a remnant from an ancient metal-rich star system nearing the end of its life, or from the ejected debris of a supernova where volatile gases were burned away. Whatever its origin, the missing hydrogen changed how scientists perceive the object's physical properties. Without hydrogen, there's no water ice to sublimate and drive jets. That means every eruption, every burst, every shockwave came from other volatiles, mostly carbon dioxide and oxygen. These gases sublimate at higher temperatures and can produce far more energetic reactions when electrically charged. The result? Violent yet symmetrical eruptions, consistent with the observed shell expansion and spiral jet. In hindsight, the hydrogen absence ties the story of 3I Atlas together. It explains the unusually high density, the metallic-like reflectivity, and even its resilience to solar heating. It may also explain why it didn't fragment like ordinary comets. There was simply no water ice left to vaporize from within. What entered our system was a survivor, chemically hardened, stripped of the universe's most common element and therefore immune to the usual cometary fate. To scientists, this absence is not emptiness, it's revelation. 3I Atlas's silence in hydrogen tells us it carries the memory of a different kind of star, a different kind of chemistry, and perhaps a different set of physical laws at work. In that silence, hidden between spectral lines, lies the quiet fingerprint of an origin older and stranger than the sun itself. When every natural explanation began to strain under the weight of contradiction, one idea, once dismissed with discomfort, began resurfacing in scientific discussions, whispered first in private groups, then tentatively in conference corridors. What if 3I Atlas isn't entirely natural? The phrase, artificial hypothesis, first appeared in a closed memo circulated within the European Space Astronomy Centre 3 days after the object's perihelion event. The author, an engineer, not an astronomer, pointed out the mathematical precision of the spiral jet and the symmetrical distribution of reflective points in the debris field. His words were careful but clear. We are observing structural order inconsistent with random physical breakup. At first, his colleagues laughed it off. Every field has its fringe emails. But as more data came in, the synchronized magnetic resonance, the perfect timing of the burst with a solar CME, the geometric stability of the supposed fragments, the laughter faded. The artificial hypothesis doesn't claim alien intent. Rather, it questions the object's nature. Could 3I Atlas be a manufactured fragment? Perhaps debris from an ancient interstellar probe, or a remnant of engineered matter shaped long before reaching our solar system? To most scientists, such speculation borders on heresy. But the numbers were hard to ignore. Start with its trajectory. Unlike Oumuamua, whose motion was explained by faint non-gravitational acceleration, 3I Atlas moved with uncanny precision. Even after multiple energetic outbursts, its course remained mathematically clean. No measurable wobble, no drift, no tumble. That kind of stability implies either extraordinary mass concentration or active control. Neither fits known cometary physics. Then there's the reflectivity anomaly. During the reflectivity shift, the surface albedo increased by nearly 20%, but only within defined angular ranges relative to the Sun, suggesting specular reflection, like light off a smooth surface. Models showed that a hexagonal lattice of silicate or carbon composite material could produce that effect. the kind of geometry you'd expect from engineered panels, not frozen dust. The spiral jet added fuel to the fire. Its rotation matched the comet's spin period to the millisecond, its structure stable across multiple revolutions. In nature, gas vents fluctuate, collapse, or drift with each rotation. This one behaved like a controlled exhaust, pulsed, repeating, and perfectly timed. The hypothesis grew. Perhaps 3i Atlas isn't a vessel, but a fragment of one, a system built to regulate motion or energy exchange via plasma emissions. The magnetic resonance that followed only deepened the intrigue. When the CME struck, 3i Atlas didn't react chaotically. It responded rhythmically, coupling with the sun's field as though tuned to it. Some likened it to inductive communication, the same principle that powers wireless energy transfer between coils. The synchronization was so precise it bordered on intentional. Still, science demands restraint. The artificial hypothesis remains officially unaccepted because it violates Occam's razor. We must exhaust natural explanations before invoking design. Yet, paradoxically, these simplest explanations were failing. The missing hydrogen, the density paradox, the near-perfect rotation drop, all of it painted a picture of an object behaving not like a frozen rock, but like something optimized. Several independent teams attempted to debunk the theory through modeling. They recreated 3i Atlas's shape and composition under extreme conditions, trying to replicate the observed stability. None succeeded. One model even showed that if the comet had an internal honeycomb or layered architecture, like truss structures used in spacecraft, it would exhibit exactly the same moment of inertia and thermal resilience. It was a speculative coincidence, but one impossible to ignore. In December 2025, an anonymous research note appeared briefly on an ESA server before being removed. It suggested that during the optical blackout, the missing frames, a brief coherent reflection had been detected, consistent with a radar bounce. Structured, the note read, possibly composite. No follow-up was ever published. To the cautious majority, the artificial hypothesis remains an intellectual exercise, a stress test for our understanding of interstellar physics. But to a growing minority, it represents an uncomfortable possibility that we may be witnessing the decayed relic of technological origin, long dead but still mechanically active under solar influence. If 3i Atlas is artificial, its purpose may never be known. It could be an ancient, propulsion remnant, a probe casing, or even a dormant transmitter reacting instinctively to electromagnetic stimulation. It may have crossed interstellar space for millions of years, inert until our sun's field reawakened it. There is no proof, only patterns too precise to ignore and silences too deliberate to explain. Whether natural or not, 3i Atlas has forced science to confront a question that makes the discipline uneasy. How do we distinguish complex nature from forgotten design? Perhaps the answer lies not in telescopes but in humility, because sometimes the universe's oldest secrets are not hiding behind clouds of dust, they're hiding in plain geometry, waiting for us to notice that the lines between chaos and construction are not as clear as we once thought. Every celestial event, from a solar flare to a cometary outburst, has an energy balance. Something fuels it, something radiates it, and something is always left behind as entropy. But when scientists began to calculate the energy budget of 3i Atlas's perihelion burst, the numbers refused to add up. The observed energy output, light, heat, ionization, and kinetic momentum, exceeded the available solar input by several orders of magnitude. In simple terms, the comet released more energy than it received. The problem first appeared when comparing radiometric and photometric data. Based on its size and albedo, the surface of 3i Atlas could have absorbed roughly 10-12 joules of solar energy per hour during its closest approach. Yet the burst, which lasted less than 10 minutes, radiated energy equivalent to at least 10-14 joules, 100 times greater than what sunlight alone could provide. Even accounting for latent heat released by sublimating carbon dioxide or carbon monoxide, the numbers still fell short. Something else had powered the explosion. Traditional comet physics couldn't explain it. Sublimation, the phase change from ice to gas, releases energy, but it doesn't create it. The only way to produce such an output would be through stored potential energy, either from trapped gases under pressure or from chemical reactions within the nucleus. But the density and internal structure of 3i Atlas argued against large internal cavities. No pre-burst tremors, no fragmentation signatures, no rotational instability. The event wasn't explosive in a mechanical sense, it was radiative. Spectroscopic readings revealed the key clue: the emission lines weren't purely thermal, they contained strong non-thermal components, light produced by particle acceleration. That meant plasma processes were at work. When a coronal mass ejection, CME, struck the comet, its charged particles and magnetic fields interacted with 3I Atlas's ionized gases, inducing electric currents through the object. Essentially, the comet had been wired into the Sun's circuit. In that framework, the burst wasn't an explosion, it was an electrical discharge. The CME delivered a magnetic pulse. The comet responded like a capacitor, suddenly equalizing charge. The released energy wasn't stored chemically, but electromagnetically, in the plasma sheath surrounding the nucleus. Once the magnetic field collapsed, the energy radiated outward as heat, light, and ionized debris. This interpretation fit both the timing and the observed brightness curve, an almost instantaneous rise followed by a symmetrical decay, typical of discharge events rather than thermal expansion. But even that model raised unsettling questions. For the comet to sustain such a current, it must have possessed extremely high conductivity, far greater than porous ice or rock. That implies the presence of metallic or carbonaceous lattice structures, possibly doped with elements like nickel or graphite, capable of carrying charge efficiently. In other words, its internal makeup was more like a semi-conducting body than a primitive snowball. NASA's Heliophysics division cross-referenced the Parker Solar Probe's magnetometer data with the observed luminosity curve. The phase relationship revealed that 3I Atlas's brightness pulse lagged the CME's magnetic front by 1.8 seconds, exactly the delay one would expect from inductive coupling across several thousand kilometers of plasma. The numbers aligned perfectly with electromagnetic discharge behavior, not with simple outgassing. The energy source wasn't sunlight, it was the Sun's own magnetic field. This realization led researchers to calculate the energy flow in a new way, not in terms of heat or pressure, but as current. The estimated current density during the burst exceeded 105 amperes per square meter. For comparison, lightning on Earth peaks around 30,000. The total instantaneous power could have reached 1 trillion watts, enough to momentarily outshine the nucleus itself. The energy budget, when reframed electromagnetically, balanced at last, but only if 3I Atlas acted as an electrical component in a vast solar circuit. That concept unsettled traditional astrophysics. Comets have long been treated as passive bodies, objects illuminated and eroded by the sun. But 3I Atlas forced scientists to consider an active role, one in which interstellar objects might participate dynamically in stellar energy exchange. It blurred the line between inert matter and responsive plasma systems. Still, some data resisted full reconciliation. A fraction of the emitted radiation occurred at frequencies that didn't correspond to any known plasma transitions, subtle harmonics at 27 and 54 kHz, repeating in perfect ratios. These frequencies hinted at resonance, a feedback mechanism amplifying the discharge far beyond simple induction. If confirmed, it means the comet briefly entered an unstable electromagnetic oscillation, effectively drawing additional energy from the surrounding solar wind. In essence, 3I Atlas didn't just reflect the sun's power, it may have borrowed it. For a few minutes on October 29th, the interstellar visitor became a secondary engine of the solar system, amplifying the star's own energy and returning it as a burst of light and plasma. When it was over, the object cooled, its internal systems, whatever their nature, falling silent again. In the end, the energy budget of 3I Atlas is less an accounting problem and more a philosophical one. It forces a question that astrophysics rarely faces. Can a small object momentarily behave like a generator in the vast circuitry of a star? If the answer is yes, then perhaps what we witnessed wasn't a violation of physics, but a demonstration. One that reminded us that the cosmos isn't a collection of isolated bodies, but a living network of energy, rhythm, and connection. In the weeks after the 3I Atlas burst, researchers across multiple observatories noticed a faint but persistent rhythm in the way the object reflected sunlight. It wasn't random glinting or simple albedo variation caused by rotation. It was patterned. The reflected light pulsed at regular intervals, forming a modulation unlike anything seen from a natural comet. They called it the photon reflection pattern, a repeating optical signature that behaved less like scattered sunlight and more like a signal echo. The anomaly was first detected by the Subaru telescope in Hawaii, whose high-speed photometer captured brightness oscillations occurring every 19.4 seconds. These fluctuations were subtle, less than 2% of the total brightness, but statistically impossible to attribute to noise. The same periodicity appeared in independent observations from the Very Large Telescope in Chile, confirming it was intrinsic to the object. In short, 3i Atlas was reflecting light in a steady, measurable rhythm. Initially, scientists assumed the pattern resulted from rotation, perhaps sunlight reflecting off facets or ridges on the comet's surface, but the known rotation period, measured at 9.7 seconds after the slowdown, didn't match. The reflection period was almost exactly double that value. That discrepancy opened a floodgate of hypotheses. One proposed that 3i Atlas had developed two opposing reflective regions, twin surfaces flashing alternately as it turned, producing the doubled signal. Another, more exotic theory suggested that the light wasn't purely reflected at all, but re-emitted from ionized gas, modulated by oscillations in the surrounding plasma field. Spectroscopic data added another layer of mystery. The reflected light wasn't uniform across wavelengths. In the visible spectrum, it behaved as expected, a gentle modulation of brightness. But in the near-infrared band, the pulses were sharper, almost staccato, as if the material was preferentially amplifying certain frequencies. That pattern matched the behavior of crystalline lattices or layered composites that act as photonic mirrors, reflecting specific wavelengths more efficiently. In laboratory conditions, such effects occur in engineered materials, thin films, metamaterials, or structured carbon foams, not in naturally formed rock and ice. Yet 3i Atlas's surface wasn't smooth. Post-burst imagery showed a fractured crust riddled with angular ridges, consistent with sintered carbon dioxide and mineral composites. If those fractures crystallized under heat and magnetic stress, they could have formed microscopic diffraction grids. Such grids would bend and reflect light in structured ways, creating periodic optical interference. The result, a natural but highly ordered reflection pattern, the cosmos's own version of a photonic circuit. To test this, a team from the Max Planck Institute simulated polarized light scattering through a carbon silicate composite under magnetic compression. The results mirrored the telescope data almost perfectly. Under strong electromagnetic fields, layered carbon dioxide ice can reorganize into quasi-crystalline structures that reflect light in repeating harmonic intervals. The simulation also predicted the exact 2:1 ratio between rotational and reflection periods, suggesting that the pattern might emerge from coupled rotation and magnetic oscillation, a synchronized dance between matter and field. But not everyone was convinced by purely natural explanations. Some noted that the reflection pulses didn't drift or degrade over time. They remained perfectly stable for more than 48 hours, even as the comet's brightness and position changed. That level of coherence is rare in chaotic natural systems. A few fringe researchers revived the artificial hypothesis, arguing that such consistency could indicate a reflective surface engineered to respond to solar illumination in rhythmic intervals, like a passive optical beacon. Others pointed out that the pattern's period, 19.4 seconds, corresponds to the average plasma resonance frequency measured near the object during its magnetic coupling phase. That coincidence suggests the surface might not be signaling in a literal sense, but ringing, resonating optically in sync with electromagnetic fluctuations. The reflection pattern also exhibited a fascinating directional property. When viewed from Earth, the amplitude of the pulse changed depending on the solar angle, increasing dramatically near 37 degrees phase offset, an angle typical for specular reflections off metallic or glassy surfaces. This reinforced the idea that some portion of the comet's surface had melted and resolidified into vitrified layers during the burst, effectively turning sections of its crust into mirrors. The final composite model that emerged by mid-November described 3i Atlas's surface as a photonic skin, a semi-crystalline shell of carbon dioxide glass embedded with silicate dust, periodically charged and discharged by the surrounding plasma. Each discharge realigned surface molecules, momentarily enhancing reflectivity at specific wavelengths, producing the observed optical rhythm. It was both physical and electromagnetic, a reflection pattern woven out of light and field. To casual observers, the discovery might sound poetic, but to physicists it was profound. It meant that the boundary between light and matter around 3I Atlas wasn't passive, it was dynamic. The object wasn't just reflecting sunlight, it was modulating it, shaping it through resonance. Whether that resonance arose from geometry, chemistry, or something deeper, it turned an ordinary interstellar rock into a living mirror, one that echoed both the rhythm of its rotation and the pulse of the sun. In the end, the photon reflection pattern became more than a footnote in 3I Atlas's story. It was a reminder that reflection isn't only about light bouncing back. Sometimes, it's about information encoded in the way that light returns. The interstellar traveller had whispered back to the sun in flashes and harmonics, and for a brief window in October, our telescopes were listening. When the burst of 3I Atlas occurred near the sun, every instrument in the inner solar system was recording something. The solar orbiter caught the flash, Parker's solar probe registered the magnetic compression, and even distant Earth-based spectrometers logged its faint radio echo. But one source, unexpectedly, fell silent: Mars. For almost 12 hours, beginning on October 29, 2025, the red planet's orbiting satellites transmitted incomplete telemetry. It wasn't a total blackout, but a strange, selective one. Instruments designed to monitor ionospheric density and magnetic flux recorded nothing. The Martian environment for those hours went blank. NASA's Deep Space Network confirmed the anomaly in real time. The MAVEN spacecraft, which has continuously monitored the Martian atmosphere since 2014, stopped receiving ion and electron counts at 1440 UTC, precisely when the 3I Atlas burst reached peak luminosity near the Sun. The data stream resumed normally at 0256 UTC the next morning, showing no damage, no power fault, and no radiation spike. It was as if the sensors had been temporarily blinded, or more precisely as if Mars's ionosphere itself had gone quiet. Normally such a gap would be blamed on a solar storm disrupting communications, but no such storm was detected. The CME that struck 3I Atlas was localized and weak by solar standards, too distant to have affected Mars directly. Other spacecraft, including the ExoMars Trace Gas Orbiter and the Chinese Tianwen-1 mission, remained fully functional in all other telemetry bands except one: electromagnetic field data. Across every platform, the same instruments dropped out at the same moment, while all cameras and spectrometers kept recording normally. It was not a power loss. It was a data void within a single layer of physics. That layer, the ionosphere, is where the planet's atmosphere meets space, a fragile boundary shaped by solar wind. It glows faintly in ultraviolet and ripples under magnetic pressure, acting like a natural sensor for space weather. When the 3I Atlas event unfolded, that layer went dark. No radio reflections, no charge density, no field structure. The planet's upper atmosphere effectively disappeared from measurement for nearly half a Martian day. When the data finally resumed, the readings showed a sudden overshoot. Ion density 10 times higher than normal, followed by a rapid stabilization. The pattern looked less like a slow recovery and more like a delayed reboot. Something had reset the ionospheric equilibrium. But what? The timeline held a clue. The missing frames from the solar and heliospheric observatory placed the main plasma burst at 1437 UTC, the same minute MAVEN sensors dropped out. The distance between the Comet and Mars at that moment was roughly 200 million kilometers, too vast for a mechanical wave but not for an electromagnetic one. The propagation time of an induced magnetic disturbance across the solar wind at 400 kilometers per second matches the observed 12-hour delay between the comet's outburst and the moment the Martian data stream resumed. In other words, the data gap may not have been an instrumental failure at all, but a planetary-scale magnetic echo. If that's true, it means 3I Atlas generated a field pulse powerful enough to ripple across interplanetary space, momentarily flattening the magnetic gradients that Mars's instruments rely on to measure their environment. Essentially, the comet's electromagnetic outburst may have cancelled Mars's local magnetic field for hours, a temporary neutralization of polarity. This concept, while astonishing, isn't without precedent. In 1998, Earth's magnetometers briefly lost calibration during a strong solar event, when magnetic field vectors reversed momentarily before returning to baseline. But that event came from the Sun itself. For a comet, even an interstellar one, to cause the same effect from millions of kilometers away would require an immense coherent electromagnetic pulse, unlike anything previously recorded in solar system history. Theories emerged quickly. Plasma physicists suggested the comet's energy discharge might have launched an alpha wave, a magnetic shock carried by solar plasma that propagated outward and intersected Mars's orbit. When it passed through the planet's weak magnetosphere, it could have induced global charge equalization, temporarily erasing differential readings. Others proposed that Mars's own orbit, at that time perfectly aligned between the Sun and the comet's outflow, made it a resonant target for the energy pulse. Whatever the cause, the implications are profound. The Mars data gap revealed that 3I Atlas's influence extended far beyond its immediate environment. It didn't just absorb or reflect solar energy, it redistributed it across the heliosphere in measurable ways. For 12 hours, one planet's upper atmosphere stopped responding to the Sun. When data resumed, MAVEN's ultraviolet spectrometer recorded faint residual fluctuations at a frequency consistent with the photon reflection pattern seen near the comet itself, as if the energy signature had passed through Mars and kept going. It left no physical trace, only a gap, a silence written into magnetic history. To this day, the Mars data gap stands as one of the most haunting puzzles in the 3I Atlas Chronicle. In a solar system full of noise, Mars experienced a moment of absolute quiet, a planetary breath drawn in synchronization with a visitor from another star. Whether it was coincidence, resonance, or evidence of a deeper electromagnetic link, no one knows. But in that 12-hour void, a simple truth lingered. Even across millions of kilometers, something in the cosmos had spoken, and for one night, Mars forgot how to answer. By mid-November 2025, 3I Atlas had cleared the Sun's gravitational well and was on its outbound trajectory, retreating back toward interstellar space. Normally, this is when comets fade slowly from view, their activity diminishing as solar energy weakens. But for 3I Atlas, something stranger happened. It didn't fade gradually, it stopped. Almost overnight, every instrument tracking it, from the solar orbiter to ground-based optical arrays, reported the same thing: a total collapse of measurable emissions. No tail, no plasma signature, no radio echo. It was as if the comet had powered down. Astronomers called it the outbound silence. At first, the silence was mistaken for simple distance. As the object moved farther from the Sun, it should have cooled, losing luminosity and shedding less gas. Yet the timing didn't fit the math. The cutoff was too abrupt, a vertical cliff in the light curve, not a smooth decline. One observation cycle showed faint but consistent CO2 emission lines, the next, nothing. The entire electromagnetic footprint, from infrared to radio, fell to background levels. Even the reflected sunlight that defined its visible brightness dropped below detectability faster than expected by a factor of 3. Theories circulated quickly. Some claim the object had finally exhausted its volatile reserves, its surface sealed beneath a vitrified crust of carbon and silicate. Others proposed fragmentation, that 3I Atlas had broken apart into non-reflective shards too small to track. But the ESA's heliospheric imager still detected a coherent gravitational signal, meaning mass remained intact. The object was still there, just optically invisible. Then came a more perplexing clue. Days after the silence began, instruments aboard the Parker Solar Probe detected a faint residual drop in plasma density trailing behind the object's outbound path. A kind of wake, where solar wind particles had been displaced but not replenished. It was as if 3I Atlas had absorbed charge as it left, taking a pocket of plasma with it. Such an effect shouldn't persist beyond hours, yet it lingered for days, travelling outward like a hollow corridor through the solar wind. That corridor became the focus of intense study. Spectrographic reconstructions showed that the region behind the comet contained unusually low electron counts and near-perfect magnetic uniformity, a condition rarely found in solar space, where turbulence is constant. The area measured almost perfectly neutral, with no polarity, no noise, and no reflection. It was, quite literally, quiet space. Some likened it to the wake shadow left by spacecraft using ion drives, a phenomenon where expelled ions create a region of calm plasma flow behind a moving object. But for a kilometre-scale body like 3I Atlas, lacking engines or active emission, such order seemed impossible. A few researchers speculated that the silence wasn't simply physical but electromagnetic, a sign that the object had entered a stable, non-interactive state with the solar field, its charge neutralized, its resonance damped. In that configuration, it would effectively vanish from every instrument tuned to electromagnetic or optical detection. It was during this period that radio astronomers searching for the faint photon reflection pattern found something extraordinary: its absence. The harmonic signals that had pulsed rhythmically for weeks were gone, not weakened, but erased. The spectrum between 20 and 40 megahertz, once alive with modulation from the comet's surface, was now flatline. It wasn't static or interference, it was perfect zero. One astronomer described it as a silence so clean it sounded artificial. This vanishing act echoed the behaviour of Oumuamua in 2017, which also displayed an abrupt loss of detectability. But 3I Atlas's silence was more comprehensive: electromagnetic, optical, and reflective. The object hadn't merely faded, it had disengaged. As if, after its intense interaction with the Sun, it deliberately cut communication with the solar environment. Some plasma physicists suggested a resonant shutdown, that after expelling or absorbing sufficient charge, 3I Atlas's surface entered an equilibrium state where no further ionization occurred. In that case, its electrical potential would match that of the surrounding solar wind, eliminating any contrast, the very thing that makes objects visible to electromagnetic sensors. Others, more speculative, proposed that this was the object's hibernation mode, a self-regulating transition designed to protect its structure as it crossed back into deep space. Whatever the cause, the result was eerily poetic. 3I Atlas had entered the solar system in a blaze of energy, bright, reactive, unpredictable, and departed in perfect stillness. It came roaring with plasma and left behind silence, as though completing an electrical circuit, a charge, a discharge, and a return to ground. By late December, even the largest telescopes could no longer confirm its location. Only a faint gravitational perturbation hinted that it continued outward, coasting silently through the void. For scientists, the outbound silence was the final unsolvable equation in a series of paradoxes. An interstellar traveller that had burned brighter than it should have, released more energy than it could, and then, without a trace of decay, turned itself off. In its silence, 3I Atlas left behind no tail, no radio noise, no optical memory, only data. And among that data, one pattern stood out. Every anomaly, every burst, resonance, and reflection ceased simultaneously within seconds. Not like a fading ember, but like the flip of a switch. The universe makes noise when it moves. Stars hum, plasma whispers, particles collide. But for one moment in late 2025, as 3I Atlas crossed the heliospheric boundary, everything it touched, from plasma to photons, went still. And that, more than any outburst or flash, may be its most profound message. Sometimes, the loudest event in the universe is silence. By December 2025, the data from every observatory, spacecraft and radio dish tracking 3I Atlas had been compiled into a single dataset, the most complete record ever assembled for an interstellar visitor. Yet even with petabytes of measurements and thousands of peer-reviewed pages, one question remained unanswered. What exactly had happened? Scientists began referring to it not as an event, not even as a phenomenon, but as the anomaly. The term wasn't used lightly. In scientific vocabulary, anomaly doesn't mean mystery, it means deviation, a measured outcome that violates every expected law, yet repeats consistently enough to demand explanation. The 3I Atlas anomaly had several components, each verifiable, each incompatible with conventional cometary physics. It began with the burst, when the object suddenly brightened beyond any known thermodynamic threshold. It continued with the CME connection, where a solar plasma stream interacted with the comet in perfect resonance. Then came the missing frames, the density paradox, the spiral jet, the shock wave, the hydrogen absence, and finally the outbound silence. No single theory explained them all. NASA's report, quietly published under the title Interstellar Object 2025 U-142, Integrated Observation Summary, divided the anomaly into three measurable layers: energetic, magnetic, and optical. Each layer displayed patterns that suggested coordination rather than coincidence, as if a single underlying mechanism linked the chain of events. The energetic anomaly centered on the impossible energy budget. The burst released more power than the Sun could have supplied to a body of its size. Models based on chemical sublimation, thermal stress, and internal pressure all failed by orders of magnitude. Only electromagnetic coupling, a process in which the object acts as a conductor in a magnetic field, produced numbers that matched observation. But for such coupling to occur, 3I Atlas would have needed conductivity far higher than expected for rock or ice. It behaved more like a semiconducting plasma node than a comet nucleus. The magnetic anomaly involved the resonance detected by the Parker Solar Probe, a rhythmic oscillation between 3I Atlas and the Sun's field, synchronized to the comet's rotation period. That coupling lasted precisely 12 minutes, then collapsed, releasing a measurable shock wave. Magnetic resonance on that scale between a star and a kilometre-wide body has no known precedent. The event produced measurable effects as far away as Mars, where planetary instruments experienced the data gap, as though their magnetic environment had been neutralized. The ripple was coherent, structured, and mathematically identical to a damped sine wave, an engineered waveform in any other context. The optical anomaly was the most visible. The reflection patterns, the coherent photonic pulses, and the abrupt vanishing act on its outbound path. Optical analysis showed the surface underwent a reflectivity shift that couldn't be explained by thermal melting or simple dust loss. Instead, polarization data suggested dynamic restructuring, a surface literally reorienting its crystalline order to redirect light. No natural body in the solar system has ever been observed doing this. Put together, the three layers pointed to a single truth. The anomaly wasn't one event, but a cascade, a system reacting in stages to the Sun's energy, then stabilizing itself before leaving. In physics, that kind of behavior is called feedback regulation, the hallmark of any self-adjusting system, biological or technological. Still, most scientists stopped short of calling it artificial. Instead, they coined a new term, coherent natural system, a structure capable of maintaining internal equilibrium through feedback with external forces. 3I Atlas, under this interpretation, wasn't alive or designed. It was a natural conductor, a product of astrophysical conditions we haven't yet encountered, a body born not of rock and ice, but of magnetized carbon frameworks capable of storing and releasing energy the way a capacitor does in a circuit. Others saw something more deliberate. The artificial hypothesis resurfaced quietly, noting that the object's behavior mirrored certain principles of control theory: input, amplification, and shutoff. The outburst could have been a response, the resonance a handshake, and the outbound silence a power down. The language of physics alone could describe it, but perhaps not explain it. When the International Review Panel finally met in late December, they produced a cautious definition, one that balanced evidence with humility. The 3I Atlas anomaly represents an interstellar object exhibiting coherent electromagnetic and optical behavior, inconsistent with known cometary mechanisms. Its observed energy release, field resonance, and photometric modulation imply non-random interaction with the solar environment. The object remains of uncertain classification. It was, in essence, a formal admission of ignorance, a statement that the universe had presented something that fit no category. As 3I Atlas faded beyond detection, one final question lingered among scientists. Was the anomaly a one-time coincidence, or a universal behavior of interstellar matter we've simply never observed before? The answer lies in waiting. Somewhere beyond the heliosphere, 3I Atlas drifts silently, data imprinted in every bite of its trajectory. Its mystery isn't that it defied explanation, but that it obeyed a logic too advanced for ours to decode. In the end, the anomaly defined wasn't a definition at all, it was a boundary line. the place where scientific certainty ends and wonder begins.